Good afternoon, everybody. How are you all doing despite today's warm weather? Good? Lucky you're here indoors, staying cool. Please make sure you stay hydrated. We have water, coffee, etc. It is a pleasure to welcome you to the 2024 Yale-Korea University Forum. My name is Dr. William Stewart, and I'm an Associate Director in the Office of International Affairs here at Korea University. While today may be the first forum for those of you in attendance, this afternoon actually marks the second forum of this event. It is, again, an honor to be here with everybody, and I was also at the first forum with President Kim at Yale last year, and who is the host of this year's forum. I'd also like to take a brief moment to recognize many of the leadership that are in attendance today from Korea University, including EVPU, VP Lee for Research, and Vice President for International Affairs, Professor Song. Before we begin, I'd also like to introduce today's speakers for the forum. From Yale University, we are joined by Professor Jae-Hong Kim. Good. And Professor Gary Broderick. On behalf of Korea University, we are joined by Professor Seung-Kwan Hong. Professor Jun-Hong No. And then, he's not here yet, but later we will be joined by Professor Sang-Hyuk Im. Well, when he comes, be sure to applaud. So without further ado, it is the moment to officially open the forum, and it is my distinct pleasure to welcome Professor Dong-Won Kim, the president of Korea University, to share a few welcoming words with us. Let's give him a warm round of applause.
This warm day, the climate change is the right subject to discuss, I guess. Ladies and gentlemen, honorable guests, esteemed colleagues from Yale and Korea University, distinguished speakers and students, it is my great pleasure to welcome you all to Korea University for the annual Yale-KU Forum. Actually, this is the second one. Last November, we held the first of these scholarly discussions at Yale in the Sterling Memorial Library. There, academics and students critically discussed and examined Korean entertainment and media, which featured Professors Hae-Rin Shin and Ji-Hoon Park from Korea University's School of Media. Today, at the second forum, we gather under the theme Energy Water Nexus, Innovative Climate Technology for a Sustainable Future Against Climate Change, a topic of profound significance to our global community, as we witness today. As a Korea University, at Korea University, we are deeply committed to addressing the pressing challenges posed by climate change. And this forum provides an invaluable platform for us to exchange ideas, share groundbreaking research, and explore practical solutions that bridge the crucial intersection of energy and water management. As we delve into innovative technologies and sustainable practices, let us remember that our collaborative efforts here will contribute significantly to a resilient and sustainable future. The insights and strategies we develop today will not only benefit our respective institutions and nations, but will also serve as a beacon of hope and action for the global community. I'm confident that this forum will foster meaningful dialogue, inspire innovative thinking, and strengthen the bonds between Yale and Korea University. Together, we can drive the change necessary to safeguard our planet for ourselves and future generations. Thank you.
Thank you for those remarks, President Kim. Before we actually start the forum, I'd like to invite President Kim, as well as some of our distinguished guests, our forum speakers, as well as EVPU, the deans, and vice presidents to take a commemorative photo on stage. So if you would. Thank you so much. This now will officially mark the start of the second Yale-KU Forum, and Professor Sung-Hyun Won will now begin facilitation of the forum's 5 sessions, starting with session 1 on the future of seawater desalination. Professor Won, the forum is yours. Let's give Professor Won a warm round of applause.
Thank you for the nice introduction. My name is Sung-Hyun Won, an associate professor at School of Health and Environmental Science in Korea University. As the topic of Yale and Korea University is focused on water energy nexus, so we have invited 5 esteemed professors from Yale and Korea University. Let me introduce our first session speaker. Please welcome Henry P. Beckton Professor Jae-Yong Kim. 김재용 교수님을 모시겠습니다.
All right, it's a great honor to have an opportunity to present at this forum. We just came yesterday and I still feel jet lagged, so please wake me up if I fall asleep during my presentation. All right, so I'm going to talk about water treatment, advanced materials and technologies. The key word here is modular. That's what I'm going to explain for the rest of the talk. I want to start by thanking President Kim Dong-won and the leadership of Yale University for the invitation. So John F. Kennedy once said that anyone who can solve the problems of water will be worthy of 2 Nobel Prizes, one for peace and one for science. That's about 60 years ago, and no one got the Nobel Prize for water, but we indeed have made many changes and improvements. So we treat the water the water that you consume in this building using this conventional municipal water treatment plant. And once we use the water, we get the produced wastewater, and we use that conventional municipal wastewater treatment plant. And they are typically in a pretty large scale that consist of many large-scale unit operations. And if you ever learned environmental engineering, this is the subject that you learn. But this is conventional, but we've been making quite some progresses in advancing different type of unit operations, such as ozonation, membrane, UV radiation, and etc. Membrane in particular is widely used, that is now used to desalinate seawater and brackish water to produce fresh water. So these are in large-scale systems, and water has to be distributed. Above the ground, we have these facilities to treat water, but under the ground, we have this large-scale water distribution network. It consists of thousands of miles of transmission pipe made of different materials. Is like interwoven structure, and has many other structures such as booster pump, chlorination system, and the storage facilities. Some say it is one of the most complex and largest scale chemical and biological reactors. If you are in the chemical engineering major, you are familiar with the concept of reactor. But this reactor has a one inlet, okay, where the water comes in, and millions of outlets, and water flow changes over time. And there are complex chemical and biological reactions happening, some chemical reactions leading to the formation of disinfection byproducts such as chlorinated carcinogens, and biological reactions such as biofilm formation. So you get the concept here. We have a large-scale systems connecting, transporting water from treatment to the waste disposal. So one way to look at our current system is that our 20th century water treatment systems are linear. So what that means is that we start by capturing water from the nature and we purify it by removing pollutants or salt. And then we distribute so that consumers, such as people like you and industry use. And then we recollect it and then we treat it to remove bad stuff and then release back to the nature. So very linear system. So this is what we've been doing pretty well over past many decades. Okay, and but the problem is now with climate change, with other many uncertainties. The question is whether this system or this approach is going to be sufficient enough to secure a resilient water supply for 21st century. So this is the question that a lot of people are asking. And the particular challenges are related to increasing demand because of the population growth and economic growth. I know in Korea, population growth is an old story. But if you think about urban systems, there is indeed a population growth in many sectors of the country, even in Korea. And there's another important aspect, which is increasing water stress because of pollution. You all heard about the nasty stuff that you have in water. And I was just listening TV commercial since I came here, and they're selling this bottled water without microplastics. I'm sure you heard about this commercial. And also aging infrastructure. So what are we going to do with all these pipes and systems that are buried underground? It's only a few decades or so. Are we going to really dig out and rebuild entire cities' infrastructure for the water distribution? And most importantly, climate change. And we are today experiencing climate change. The Seoul used to be not this hot during June, but it was scorching today. Anyhow, so because of this, a lot of people in the field are thinking about this integrated urban water infrastructure. So what that means is a network of both centralized and distributed water treatment facilities to supplement the conventional system for reclaimed water for this use for both potable and non-potable purpose. So as this picture shows, we have the source treatment, but we do have some clusters where the water is treated in decentralized fashion. And in order for us to do this, and there are, the way we design the water treatment system should be different from our previous Victorian large-scale systems. Okay, so this is one of the example schematic for such water treatment, where we have a small-scale systems that treat for a fit-for-purpose application. For example, you have a certain target in your wastewater recycling scheme. You use a certain fit-for-purpose module. When I talk about the module, you might have, especially young people must have heard about this modular cell phone. Right? You change your cell phone only a few years because you're not happy about everything about your cell phone, but because you need a better camera for your Instagram, right? Or more storage. But so the idea is that you have this baseboard and you have a modulator function in the cell phone, but you can just upgrade the camera. That's called modular cell phone concept. I'm just showing this to you because I think you understand this. But same is true for these modular water treatment technologies for distributed treatment schemes. So I'm talking about this water for our consumption, like drinking water or water that you use for your shower. But then industries also need resilient and cost-effective water supply. okay, for them to remain competitive. Well, I'm just showing you guys a few example industries typically strong in America: food and beverage, primary metals, pulp and paper, oil refineries, petrochemicals, and service sectors. So if you look at all these different constituents in the wastewater, they vary from industry to industry, and they come with their own unique challenges. But if you can look at how the wastewater is treated, it is somewhat similar. The way we treat the municipal wastewater is somewhat similar to some of the industries. Of course, there are some changes depending on the uniqueness of the wastewater. Well, again, in many cases, we have this large-scale system collect wastewater and discharge back to the nature. But that's not going to be competitive or sustainable down the road, especially with the climate change. And this map shows where in the United States the waters are withdrawn for industrial purpose. And unfortunately, it somewhat overlaps with the regions with drought, depending on the season. Okay. So looking at the three industries in the United States as an example, primary metals are mostly active in southern part and northeastern part of the United States. Oil refineries are mostly in the coastal side because they have to bring, but now a lot of oil refineries are in the land because of the shale gas. And then food and beverage industries are mostly located near the population centers. Okay. The problem is that these challenges are not homogeneous. It depends on the location, and it's getting, but the precipitation and the climate change is giving different pressure to different industries. And now the water shortages in many cases, many states are causing industries to relocate, modify their process to require less water, or pay more for the water that they purchase from the municipality. Either of these is good for the industries, is their cost. So if you think about water treatment in the industry, maybe their primary target was to meet the regulation, and you may say that we want to treat the water to protect our environment, but now it's becoming more like their survivor. Okay, industries have to make changes, otherwise they cannot be cost competitive in many ways. So there are a lot of technical challenges to overcome this. There are also non-technical challenges and related to regulations and stuff like that. But I'm in engineering, so I'm mostly focused on these technologies that are for efficient, cost-effective, and modular water treatment systems. So this is again, this is from U.S. Department of Energy's recent roadmap report. U.S. Department of Energy, DOE, recently created a center called National Alliance for Water Innovation. And in order to address these technical needs, they came up with these strategies, okay, under this acronym A prime. A stands for autonomous operation. P for precision separation. R for resilient treatment and transport. I for intensified brine management. M for modular systems. And E for electrified systems. And these are related to, as I said, making systems more distributed, autonomous, and so that they can be, we don't have to rely on the Victorian style systems that we had in the past. So I've been talking about the water supplies in developed countries, and we're talking about industry. So it seems like there are a lot of water problems in the places where we live now. But let's do not forget about what's outside these developed countries. This figure shows, analyzes, x-axis here is access to electricity. You can interpret it as access to basic infrastructure, okay? Y-axis here is the access to basic drinking water services. basic drinking water service means that you can obtain water within 30 minutes of transport. Well, if you look at this graph, there's some trend. This laser point doesn't work, but anyhow, so it seems like there's a trend, right? So the regions with the rural areas with lower basic infrastructure, they tend to have more problems. At this moment, we have over 600 million people living in rural areas in low to middle income countries. Okay, still lack the access to basic drinking water. And 600 million, the population of South Korea is 50 million, and 600 million people lack the access to basic drinking water service as of now. So water problem, if you think about bad water, you drink it and you get sick and unfortunately some die, okay? But it is actually a lot more than that. In addition to health implications, it means a lost opportunity, right? So a lot of people, especially women and children, spend a lot of time collecting water in rural areas. And also that means a lot of lost opportunity for the education. So these low to middle income countries, they cannot compete with developed countries because they don't have time to catch up. And there's a lot of global security concern. Some estimate over 500 global conflictive acts related to transboundary water in the past 50 years. And some says the war of the next century could be sparked by the water conflict. And you also know that there's, you need water to produce crops. And so the food security is closely tied to how the water budget changes. And I'm sure you already heard about how climate change has been impacting what you eat these days. A lot of fish that I used to eat when I was young in Korea, they are very expensive now. And things are changing because of the water temperature change in the water surrounding Korean peninsula. All right, so that was a brief introduction for those who haven't heard about the water problems. I want to talk about my research now. My research group has been maintaining 3 different research areas because I have a diverse interest in water. But also, as a faculty, you don't know which one will get funded, so I try to maintain my budget, right? So I've been working on these 3 areas for past many years. These are somewhat related to that modular electrified, and some are related to the selective pollutant destruction technologies. So as I was preparing for this presentation, I decided not to pick one and then go deeper. Instead, I'm going to show some of my most recent and current research with a focus on just delivering the idea. Why do we do it and what that means without really touching the details. But later, if you're interested, we can discuss more. So the first one is dye-sensitized and photothermal solar disinfection. So a few years ago, we did this analysis. So we are looking at the world map. And the color means how much solar radiation you get, okay? I'm sure now Korea is red at this moment, but the red means higher solar radiation. And the dashed line means the region with lack of access to drinking water, okay? So the one thing that we notice is that the region with a lot of trouble in terms of providing water, safe water, tends to have higher solar radiation. So if you analyze data more, x-axis is solar radiation, y-axis is, again, this access to basic drinking water service. We see that, on the right lower corner, 64 countries with less than 80% rural access to drinking water service has significantly higher solar radiation than the global average. But that is a good opportunity. If we think about using solar radiation for water treatment, one thing that you can do is to get the solar photovoltaics and then connect to some sort of UV lamp or a membrane system. But that can be a little bit too advanced in many contexts because of the cost and the maintenance and operation. practice is surprisingly what's called solar disinfection. We call them SODIs. So basically, you just put water in this plastic bottle and leave it under the sun and wait. Okay, you wait for a couple of days, and you hope that the solar radiations UVB and IR to heat up the lamp, heat up the water, kills the germs in the water. Okay. Imagine that you are doing this. It's going to be somewhat hectic to really arrange all the bottles for the entire family. You don't know which one has been exposed for how long, right? And you don't know whether water is ready to drink. And most of all, it takes long, okay? So we wanted to address this problem. One of the research that we did in the past was using photosensitizer. I'm sure Professor Brookbeek, you're going to talk about photosensitizer a little bit later. Okay, but a photosensitizer is the chromophore that takes the light and it does some photochemical reaction. And we use the dye called erythrocene. Okay, erythrocene is a dye that makes the color, red color. And that sounds scary, so I'm going to add this dye to water. But this is the dye that you are consuming a lot around the world, okay? So the idea is that this photosensitizer in the water is going to take the light, okay? And then it produces reactive oxygen species and goes and kills the germ, okay? That's the concept. But some of the photosensitizers, when they take the light and get excited and produce reactive oxygen species, they photobleach over time, okay? In some of the energy field, when they use dye-sensitized solar cell, their goal is to prevent photobleaching. They want to keep the dye longer. So sometimes they use PCBM, like CCD-based photosensitizer, because they are very, very stable. But this dye is somewhat unique that they photobleach really fast. Okay, so if you put a dye in the water, it photobleaches over time under solar radiation in about 20-30 minute time scale. Okay, so what that means is that it disappears, but luckily their kinetics to kill the viruses in the water is about the same scale, time scale. What does that even mean? So the way we are imagining is that you have a bottle and then you put a pink color, and some of you may already drink colored water, like vitamin water. If you go to the convenience store, all that waters are colored, okay? So you add this pink dye and you leave it under the sun and it photobleaches within about 20-30 minutes. But because of that same chemical reaction that leads to photobleaching, it's going to kill the microorganisms in the water, okay? So, so we call it edible dye sensitized solar disinfection. So we did a lot of experiment in the rooftop of our building, and we did some simulations over the globe. So if you look at the map, in the upper map, the red color means it takes only about 10 minutes or so to disinfect 99.99% of bacteriophage in the water. So it seems doable. Well, so after that, we are thinking like, so having playing with the bottle is just probably okay, but we wanted to scale up. So this is the flow-through reactor. So we put let the water go through like a snake, okay? And then we put a dye in one end, and as water flows, if you look at the picture there, it's pinky at the beginning, but it becomes transparent after solar exposure. So you can drink the water if the water is clean. You don't drink if the water is pinky. Okay, so that's the concept. So we designed this, and we did the first demonstration in Kenya, Nairobi. And at that time, I met people in the School of Architecture, and I showed this prototype, and my colleague in School of Architecture loved it. Hey, Jae-hong, it looks like we can use it for window. So they were working on this small micro house for developing countries and disaster relief scenarios. So it's just like house in a box. You ship it and you construct it, and it has a lot of things, but you need water. You need water disinfection. So the idea was integrating that into the microhouse. And currently, we have this prototype being tested in Guatemala for disinfection of the water. This does not treat the entire water. This is for disinfection purpose only. So it has to be followed by, it has to follow pre-treatment, like filtration. Well, some may say, hey, then you still have to deliver erythrocin to the rural areas. That doesn't sound right. So we were thinking that it would be nice if you can use natural photosensitizers. Okay? Do we have a natural photosensitizers? Yeah, we do. Okay, so that's how the plant works. Okay, we are thinking about like strong natural photosensitizers, and at some point we came up with this term, phytophotodermatitis. I never heard about this before. Maybe people in the medical field knows. So what that means is that some plants have a very strong concentration of very potent photosensitizers. So this poor lamb was grazing on some leaves, and it got photosensitizer on these nodes and was walking around, get a strong sunburn. Okay, you can do that experiment today under the sun. Do you know this Corona beer? Not the coronavirus, Corona beer, right? If you go to the bar, they give the lime, right? In Korea, somehow they use lemon, but Corona beer, you should use lime. But anyhow, if you get a lime, you squeeze. Lime has a very high concentration of that photosensitizer. You squeeze it under your skin and leave it under the sun, and you get this sunburn on your skin. Okay, what's happening? These furanocoumarins in these citrus will respond to the light, and they produce reactive oxygen species, and you're going to get the skin burn. Okay, all right. If something is like burning your skin, as an environmental engineering perspective, yeah, there's a good opportunity to use that power to kill the germ. Okay, so we did quite a lot of search for different type of photosensitizers, and these are some examples. And they are coming from this different type of plants, even bug. Okay, and recently we found that there's this master plant that produces highest concentration of photosensitizers called giant hawkweed. Okay, it lives in upper New England region of the United States. It is so dangerous so that if you find it in the wild, they actually put a barrier so that you don't get in touch. So this is my PhD student who actually collecting the sample because he didn't want to get a sunburn. But anyhow, so we collect this giant hawkweed and then we extract it, but it turned out it's too difficult to process this. So we decided to do something more familiar that you can grow in your backyard in developing countries. So that's the concept called farm to tap water treatment. So a lot of people use things like alfalfa and turmeric. You use a lot of turmeric in your curries and other East Asian food. And also St. John's worts, they actually use it for the tea. Okay, so the idea is to grow this plant in the backyard. You extract the photosensitizer, put that in the water, and do faster, more efficient solar disinfection. All right, that was my, no, actually there's one more. So solar photothermal disinfection idea came in because I've been studying disinfection for quite some time. And one thing that I realized that there's no silver bullet, meaning water contains different types of microorganisms like protozoa, bacteria, and viruses, and there's no single disinfectant that can kill everything very effectively. Only universal disinfectant that we use is heat, and that's the reason why your milk is pasteurized. Okay, so the idea here is to raise the temperature of the water, but the water does not absorb light. So what we are using is the light observers such as carbon black or nanoparticles that do surface plasmon resonance and basically bring the microorganisms to the surface at high temperature, fry them. Okay, that's the idea. And this is the prototype, and we did, as an engineer, we are engineers, so we make a prototype and we do a lot of simulations. And we found that maybe around 60 centimeter by 60 centimeter under sufficient solar radiation, you could disinfect about 8 liters of water daily. Right, that's my disinfection research, and I'm going to talk a little bit about the membrane. So membrane is widely used for desalination and water treatment. And once I stumbled upon a crazy question about what to do with damaged membrane, especially when you send small filters to developing countries, there could be holes. So how do we even check the integrity of the system? What if membranes get damaged? We do not know whether microorganisms are passing through the membrane. So how do we deal with this? Okay, so that was the question. So what do you do when you get a cut in your skin? You put a Band-Aid so that your skin doesn't leak. Okay, so that's the first idea. So you have a compromised membrane, the membrane with a physical damage. We send out the particle. It goes into the damaged side and they cross-link so that they block this damage. I think now you guys are using this the glue bond. Like when you got a cut, instead of Band-Aid, you put a glue, right? It's pretty similar concept. So this is our drawing, and this is how it works. So this is a hollow fiber membrane. You cut it and you send out the particle, you cross-link, and they stay pretty stable even after backwashing. And looking at this virus remover, when there's a cut, virus start to leak. But if you send out these particles to heal, it restores its virus rejection efficiency. So we call it, you wanted to make it fancier, so we call it nano Band-Aid. Okay? So yeah, Band-Aid is great. Okay, but what's fancier is self-healing membrane, right? Our skin self-heals. Well, self-healing, I'm sure you have seen some self-healing coatings on the cell phone or card paintings. They now sell the product with the self-healing properties. But the problem of the membrane is the membrane has to be porous in nature. So if some materials start to grow and block the surface, it is very difficult to control the desired porosity. Okay, so it was certainly some contradicting goal. The way we did is, this is the first generation. So we came up with this microcapsule. We put super glue, okay, that you use, isocyanate, and then we synthesize the membrane containing a lot of microcapsules. When the membrane gets damaged, they release the glue and fix on the spot. Okay. Well, it was at least the first self-healing membrane in the literature. We had a lot of fun, but we had a lot of trouble. It was extremely difficult to make, and it doesn't last long. But it was just a good concept. We enjoyed it. And sometimes you just do it and publish and you move on, right? Our second generation was using microvascular network, basically a tube. We have a network, and then we grow the membrane on top so that the tubes provide physical strength, but at the same time, when they get broken, it releases the glue and it fixes it. Okay. So again, the synthesis was painful. It worked well, but we were unhappy about how it was functioning. On top of that, the problem is that when you use this kind of super glue, when there's a damaged side, it releases the glue and fixes it, that area becomes completely blocked. That is the first dilemma that we had, right? It doesn't work. So our third generation is actually using hydrogels. So we learned that there are this way to confine the hydrogel. You have a certain porous structure, and then you bind the hydrogel inside the pore, just right amount that it has a tendency to expand. The substrate is basically a skeleton, and hydrogel, like what you use for the diaper, they are the membrane, okay? And we control the thickness, and then water passes through the hydrogel. The good thing about hydrogel is that if you get damaged, it heals back. So now you have a membrane that poke, heal, right? So that was the first generation. I think just like that can heal back again and again and again. Well, these are the membranes that, again, with a new unique self-healing function, it is very, very far from commercialization. It's a sort of proof of concept, but this is something that we studied. Nowadays, we've been incorporating different type of polymers onto the membrane to give a very unique function that I'm not going to talk today. Going to the next research is about advanced oxidation. So some of the physical separation, you remove the pollutant by concentrating pollutants, so you produce clean water, but you are left with this concentrated stream of pollutants, which is tougher to treat. So in many cases, when you are talking about producing clean water, you want to destroy the pollutants, okay, by oxidatively or reductively. One of the oxidants that we use is hydroxyl radical, which is extremely reactive radical, but they are very, very short-lived. So what you have to do is to start with a precursor like hydrogen peroxide, which is stable, and then you apply some energy, such as UV, to activate peroxide and produce hydroxyl radical, and the hydroxyl radical goes and destroys the pollutant. And that process is called advanced oxidation. So let's imagine a small-scale water treatment system that you have for destruction of pollutant. So what's the first requirement? You have to add hydrogen peroxide, okay? Let's imagine you just purchased a water treatment unit under your sink, but the manual says you have to refill hydrogen peroxide every 1 week. You wouldn't like it, right? So can you produce hydrogen peroxide on site? Producing hydrogen peroxide, there are tons of research out there in energy field because liquid hydrogen, hydrogen peroxide is considered as a alternative liquid fuel than the compressed hydrogen. So there are quite a lot of research, but our research is not about producing high concentration of hydrogen peroxide. We are talking about concentration as it's just enough for us to produce for water treatment. So the first research that when we stepped in was to making electrochemical cell, basically a small cell that looks like this. You plug into electricity and it produces just a few millimoles of hydrogen peroxide under the current, under the water that we typically get from source water, such as surface water or the groundwater, which has a pretty low conductivity. Well, the science to reduce oxygen to hydrogen peroxide is well known, but when it goes into the water, you have tons of problem because water does not come super clean. It has many other constituents. So our research on this subject for past few years was to make sure the cathode for hydrogen peroxide production lasts long, like many, many days and months, because that itself is extremely challenging, is when you are introducing your electrochemistry to dirty water. So now we have a hydrogen peroxide synthesis cell, and then we want to activate it to produce hydroxyl radical. And now that's where the catalytic membrane comes in. So we have the catalytic membrane, starting with a ceramic membrane. We grow the catalyst, in this particular case, iron oxychloride. So we synthesize this membrane, and then we are doing this filtration of water containing a model pollutant. The kinetics is super fast. We are talking about 100% removal of this pollutant within tens of seconds within the membrane. The kinetics was much, much faster than we typically observe in bulk phase. And this is called nano-confinement effect. I could talk about this for 1 hour, but I'm going to just skip now. But this is what we've been studying for quite a few years now, that we are making many different type of catalyst on many different type of catalytic surface, catalyst substrate, metal membrane substrate. And this is one example, but recently we stumbled upon different type of catalyst on a ceramic membrane ceramic system, and our efficiency is actually pretty high. So one of my students who started as a Yale College freshman 2 years ago, he liked this idea, and along with my PhD student, third year now, they started a company last year. So the company's name is called Kitala, and they've been winning a lot of awards now. They haven't done much fundraising yet, but now they're targeting very specific industrial wastewater market to introduce this catalytic membrane system for water treatment. So the last topic, I guess I'm okay with the time, right? Is the single atom catalyst. So this is the subject that we've been studying mostly recent years, and also Professor Seung-hyun Won here, when he was doing postdoc in my group, also studied single atom catalyst. So you heard about this nanotechnology. A lot of research that I presented has some nanomaterials, and that's what we've been doing for quite some time. And the reason why we like nanomaterial, starting from bulk metal to nano, because it drastically increases the surface area, okay? And when you also make it smaller, your surface atoms have different coordination environment. They have unique catalytic properties. So we go from bulk, large, to nanoscale, and smaller and smaller and smaller. So what's the theoretical limit? Putting just single atom onto the substrate, and they call it single atom catalyst. There's a lot of controversy about the exact term for past few years, but it seems like now everybody uses single atom catalyst. So I tend to use that term. So these are example single atom catalyst, palladium nanoparticle, which look like this, 5 nanometer, but once you go below, and we are actually loading that single atom, in this case, a silicon carbide, atom by atom, you can actually see this nice discrete atom dispersion in this case. So what is the reason why people like me, environmental engineer who is thinking about water treatment, study single atom catalyst? So we stumbled upon this particular reaction. So you do have a lot of chlorinated pollutants in water. You probably heard about Daegu Penol 사건, right? Maybe you're too young. When there was like phenol release in Nakdonggang, right? And you get chlorinated, and this phenol, when chlorinated, smells bad, okay? And that's chlorophenol, okay? So the chlorinated compounds are not natural, and you want to break this carbon-chlorine bond. You want to dehalogenate, okay? So we've been studying on dehalogenation reaction, but if you do it in a nanoparticle, this reductive power goes not only onto breaking carbon-chlorine bond, but also reduce the double bonds in the other parts of the molecule. And that is a problem because when you're talking about treating water, your water has millions of different stuff, okay? And what you want to do is you're using your redox power just to break that you don't want, such as carbon-halogen bond, okay? So we found that when palladium or platinum, when it is in the single atom configuration, you use all their reduction power to dehalogenate 100%, near 100% selectivity. There are a lot of mechanisms behind this. I often work with computational chemists to understand what's going on. But in brief, you can imagine that nanoparticles are sometimes too big when you deal with a very small molecule. So that's the reason why we've been working on making different type of single atom catalysts. We start with the palladium and platinum, but then we've been studying quite a lot of different transition metals. And recently, this is actually our most recent publication that we use under what is called under potential deposition, electrodeposition to load different type of single atom transition metal single atoms, large quantity on porous electrode, porous carbon substrate. The reason why we are particularly interested in that configuration is because we want to do this. Okay, so this is our paper in review now. So you have a carbon layer. No, actually it was published. Carbon layer, and so water passes through. We have transition metals, and they reduce nitrate in water to dinitrogen, N2, which is environmentally benign. So this is focused on groundwater or surface water with some nitrate. So we call it electrified membrane, but with a transition metal single atom catalyst. So another example is hydrogen peroxide synthesis. I mentioned about this using pretty simple cathode. And you can actually, there are many options for cathode material. We use carbon nitride, or you can just simply use just carbon as a cathode. But one of the materials that we studied was carbon nitride. And we added anthraquinone as a catalyst. So anthraquinone is the most widely used catalyst in large-scale production of hydrogen peroxide that you can purchase. Okay? So you are reducing oxygen to hydrogen peroxide, but for that reduction to happen, electron has to come from somewhere. So if you look at the hydrogen peroxide synthesis in energy application, energy field, they add electron donor, such as ethanol. Okay? Well, but in our water treatment, you don't want to add ethanol unless you want to produce alcoholic beverage, right? So you don't want to add electron donor. So you want to oxidize water. The water oxidation is not that efficient. You have to have a catalyst. So oxidation catalyst, let's imagine cobalt catalyst in nano size. So it sounds simple, but then when you have anthraquinone oxygen reduction catalyst and cobalt water oxidation catalyst together, when they physically in contact, they cancel each other. Reduction, oxidation cancels each other. So it doesn't work. I did not know much about this until we started to look into this. There are quite a lot of research on how to separate reduction co-catalyst and oxidation co-catalyst. So we just happened to have carbon nitride substrate. So what we did was we add anthraquinone on the side of carbon nitride, and we add cobalt single atom in the ring, the holes of the heptazine ring of structured carbon nitride. So basically, you just load cobalt single atom one by one. Because of that structure, cobalt and anthraquinone has to be separated out. And the major finding was that the hydrogen peroxide synthesis due to oxidation catalyst and reduction catalyst was additive, not canceling each other. I think this discussion may be too much detail, but I'll be happy to explain more if anyone has more questions down the road. Another research that we've been doing a lot is environmental fate of this single atom catalyst. When we look at the papers coming from the field of chemistry or material science, especially for single atom, is widely used in dry phase. And our application is in water under redox condition. And one of the biggest questions is whether single atom catalysts will be stable over time because their surface energy is high, they just migrate around and they may agglomerate. Publication, pretty recent, we are looking at, again, 4-chlorophenol degradation using single atom catalyst. It works well with a single atom catalyst, but we found that they actually change over time. So we use a lot of X-ray from synchrotron source and Brookhaven. So we did an in situ cell, and we are looking at how the single atom changes over time as they react in the aqueous phase. And we do find that they do migrate, but not always. We still do not know the answer. For some of the transition metals, like copper, they migrate pretty good, but iron is more firm, depending on the substrate. And depending on the target reaction, their reactivity seems to change. So we don't have a clear universal explanation of this, and we are at the stage of now just looking into diverse scenarios. Well, with that, so that was some introduction of the research that I've been doing. And just want to talk about this modular system again, just bring back all these things together. So x-axis here is the scale, the larger scale, smaller scale. Y-axis is the cost and energy intensity. So it takes a lot of energy and money to transport water, okay, because of the water is heavy. So at the larger scale, conveyance cost increases, but you all know that if you make things larger, the unit cost decreases. And current, the optimum point for the levelized cost of water, we call it LCOW, is somewhere around there. And that's where we produce our municipal systems or industrial waste water treatment systems. It is very difficult to find a way to transport water at cheaper way than we currently do. Okay, it is very difficult to do that unless you move your system to the moon. Okay, so there's Earth gravity problem. So this is the area where we can technologically advance. Okay, by lowering the treatment cost for the smaller systems. If we do that by making systems on a smaller scale, then maybe our optimum may move from current to the lower, smaller scale system. And that is the system which is a lot more resilient. And as I said, with climate change and population change, we just cannot continue to rebuild the entire system. We have to we have to think about smaller modular scale systems that are more adaptable to changes in future. So I want to conclude my presentation by my wonderful research group. All the data presented here are done by my students and postdocs, not me. And I just want to say final that the Korea University has been very special to me. So 2 years ago, I had a 20th year anniversary as a professor. And I had about 10 people who are currently in academia in Korea. Two in Korea universities, Professor Sung-hyun Won and Professor Jae-sang Lee, and civil and environmental engineering. So we had this. I had my former advisors and my academic grandchildren. I see some of them here, and we had this reception at Korea University. So it's just really particular honor for me to be here and to continue to have the relationship with Korea University. Thank you so much for your attention, and I'll be happy to answer any questions that you may have, and you are welcome to speak Korean for Q&A.
Thank you for the nice presentation. I was the good student, right?
Best.
So if anyone has the question from the floor, just feel free to ask him, either English or Korean, okay?
Well, I talk to Professor Hong pretty frequently, so you're welcome to ask me questions, but I want to hear questions from someone else, okay?
I really enjoy your presentation as usual, and since there is no question from the floor, I'd like to have this question that I have. I think we discussed this one before. I mean, you mentioned in your presentation electrified water treatment systems. I also believe that in the future we'd like to have Tesla in water treatment sectors, and which can be driven by renewable energy, and that's why there is pro and cons regarding electrified water systems. Can you elaborate more about pro and cons of electrified water treatment system for the future? I mean, sustainable future.
Right. So I'm not sure if I can really answer in a broader sense, but in my case, one of the big keyword is chemical-free. The chemical-free and on-site generation of the chemical or without adding excessive chemical to drive a particular reaction, just use the redox power from the electricity is one big keyword. Probably the second is the system can be a lot smaller. And the size is actually important to make it in a distributed system. In fact, said that in other places, Korea can be the leader of this because we grew up, I grew up in Korea, so we grew up hearing from parents that do not drink water from the tap. Okay, and consequently, Korea has a big business in small home filters, so much more advanced than filter systems that I see in other countries. So if you think about these systems, they are fully electrified. Okay.
Thank you for your presentation. My name is Yeowon Kim in the Graduate School of Energy and Environment here. I'm really intrigued by the concept of using the color dye to indicate the readiness of the drinking water in the, I guess, the vulnerable regions. But since it's only for the disinfection, the water needs to be treated to be disinfected and then to be properly ready to actually drink. I'm wondering how it is really has meaningful kind of implications in like African regions, which doesn't have good like treatment facilities, I believe.
Right. So that disinfection has to follow filtration. So in typical, small villages, I haven't been to a lot of places, but I've been to some. It is relatively easy to come up with the media filters. Or in some countries, they have the ceramic pot filters. So it is relatively easy to remove particulate matter. In many cases, down to a few microns, it is not that difficult using these media filters or pot filters. The problem comes with the virus because they are tens of nanometers and they tend to pass most of the existing system, smaller system, unless you do a chlorination. I can talk about chlorination for long, but chlorination has a lot of trouble too. So we are thinking about a way to deal with virus. And this process also only works for virus. For this photosensitization produce primarily singlet oxygen, and they are not effective toward bacteria or protozoa. But it is somewhat very reactive to the viruses. So that's the reason. So yeah, we are not proposing this as a single step. No water treatment system no single system can treat everything. So it has to be always a multivariate.
And I have another question.
Okay.
Because like I have so many questions because I'm not an expert in the chemical process of the water. Another question that I had was because these waters like that you showed us in a conventional type was in a plastic bottle and then exposed to the solar radiation. And these days we talk a lot of the microplastic problems. I'm wondering if it would cause any like byproducts of the plastic from the bottle and it could cause the health problems.
Right. So I fully agree. If you, places, institution in Switzerland, there is a SODIS group, and they study a lot about how the plastics degraded over time. They release something that may be harmful. Okay. But if you think about, you are given a choice that you get diarrhea next day by drinking water, or get some carcinogens with a risk of 10 to the minus 5 over exposure to 10 years. So which one would you choose?
It wouldn't cause a serious health.
I mean, it causes serious health problem, but your immediate concern is to get rid of the waterborne pathogens. So that's why carcinogens like disinfection byproduct, it becomes a tremendous issue in the developed countries. But when you go to underdeveloped places, who cares about a little bit of carcinogens in water? Otherwise, you are going to die. You may die. You may die because of diarrhea. And significantly large number of still young people, newborns, and babies die because of diarrheal disease.
Thank you.
Yeah.
Any further questions from the floor? No.
Thank you for your presentation. I'm Taek Ju from the Department of Earth and Environmental Science. I'm also not an expert on this topic, but I have some similar side effect potential side effect questions that I was wondering through all these treatments, and you're also emphasizing all the water crisis because of the climate change. So I was kind of wanted to ask if like there could be some like any other greenhouse emissions during like applying or making all these materials when trying to do all the water filtrations.
Yeah, so there are a lot of concerns on producing CO2 from the energy that we consume for water treatment. It sounds small, but it's actually pretty significant. And you might have heard about, this, I think I saw also a news article about the data centers, okay? You need a large amount of cooling water too. And the cooling water is just not pure water, you have to treat them too, depending on the situation. So there is a lot of overlap between water and energy. I could have spent more time on that, but basically the bottom line is that you need water to produce energy, and you need energy to produce water. So, but if you think about this centralized system, in the electrical grid, traditionally we have a power plant, and we have a large distribution network, and you plug in. But for past many years, we are gradually shifting to more distributed system. I have solar panel in my house too, so we are sort of detaching from the main grid. So the way we see is as the energy get more distributed, water will also follow that same trend, because energy and water has to always go tied together, always tied together. Another interesting thing to mention is that I briefly said that the water technology roadmap was developed by U.S. Department of Energy, not Environmental Protection Agency. Why? Because for DOE's point of view, in order for U.S. industries to remain competitive, they need to continue to produce energy, they need to continue to manufacture, but water is becoming one of the major challenges. So yeah, water and energy are closely tied.
Thank you. Due to the time limit, let's wrap up the first session.
Okay, thank you so much.
Let's move on to the next session. Please welcome second speaker, Professor Gary Brupik from Yale University. Please welcome him. He is now a professor at Department of Chemistry and also director of Energy Science Institute.
Okay, thank you very much. It's a great pleasure to be here. This is my first visit to Korea University, and I'm really honored to be part of the program here. Thank you I want to really thank the organizers for the invitation to present. And I'll talk about some of the work we're doing in solar energy applications. So just a little to start out. So this is a picture of Sterling Chemistry Lab. It was built 101 years ago. We actually just last month had a centennial celebration for Sterling Chemistry Lab. It was, of course, Yale is quite an old university, more than 300 years old. But when this building was built, it was the largest chemistry building in the world. It's now quite old. And so, but we're not only working in old facilities. This is the West Campus, is where our Energy Science Institute is located. And so I'll tell you a little bit about the West Campus. But before I do that, I'd like to just give a little bit of an introduction about the significance of energy. And I hearken back, this symposium is on the energy-water nexus. And it reminds me of Rick Smalley and his end of his career. So Rick Smalley, some of you may know his name. He was the Nobel laureate. He won the Nobel Prize in Chemistry for discovering a new form of carbon, carbon-60 or buckyballs. And of course, that was a big achievement. But towards the end of his life, he became a champion for energy and water. And he listed the grand challenges facing humanity in the 21st century. Number one was energy, and number two was water. And this is what we're focused on here today. So we heard a lot about the water issue and water purification and the water challenges. I'd like to talk about energy. Now of course, most of our energy right now is coming from fossil fuels, and burning fossil fuels is a huge problem. And we're seeing it right now. The temperature here is very hot. Back in the United States, some of you may have been listening to the news, we're facing a heat dome, the largest in history right now in the United States. Most of the United States is seeing record high temperatures right now this week. And of course, this is going to continue to be a problem and get more and more of an issue because we're continuing to burn fossil fuels. So we really have to think about how can we stop using fossil fuels and turn to renewable applications. I think by most analyses, solar energy is has the most potential. Just one little factoid is there's enough solar energy striking the surface of the Earth. If we could harness 1 hour of solar energy striking the Earth, at 10% conversion efficiency, we could power the planet for a year. So there's a huge potential with solar energy. One of the big problems, however, with solar energy is it's intermittent. We don't have sun at night, don't have much sun on cloudy days. So storage is a big issue. Right now, you may know, what is the most widely used method to store solar energy? Water. So this is water. Pumping water uphill is more than 90% of storage of solar energy is done by pumping water uphill. And that's, of course, not very widely applicable, and it's certainly not possible on a local scale to be able to do that effectively. And so we'd like to be able to come up with a way of turning energy into stable chemicals, solar fuels, and that's the focus of the research that we're doing, is using solar energy to transform abundant chemicals such as water into fuels that we can store for longer periods of time and then use them when the sun isn't shining. Or also wind isn't blowing, and wind energy is also a huge potential for renewable applications. And so with that of course, all of us understand the issue of energy and sustainability. And I'd like to start out by saying a little bit about Yale's West Campus, and then I'll talk about a more specific aspect of our own research focused on water oxidation catalysis using atomically defined active sites on nanostructured materials. It's actually a little bit overlapping with what Professor Kim talked about with single atom catalysts, but we're using them for solar energy applications, in particular for solar fuel applications. And so, this doesn't seem to be advancing here. Do I have to point it this way? There it goes, okay. So Yale West Campus, just to give you a little bit of an orientation. So Yale University is in Connecticut. It's a small state in the northeast of the United States, fairly near New York City. And here is the downtown area. Here is where Yale University is located. And here is the West Campus. It's about 10 kilometers away from the main campus. It was formerly owned by Bayer Healthcare, which is a pharmaceutical company. It was their major research and development site in the United States, and they had decided to consolidate their R&D back to Europe and wanted to sell the site to a pharmaceutical company. There was no interest. Somehow Yale got involved. None of us were aware of that until it was announced that Yale had purchased the site. for 1/7 of what the asking price was. So I think our administration felt it was an opportunity too good to pass up. And it's this is the site. It's located, and here's a picture of some of the buildings. These are the Energy Sciences Institute buildings over here. The site has 1.6 million gross square feet of space with 20 buildings, 136 acres of space. It's about the same size as our entire main campus. So if any of you have been to visit Yale, we have on the north end, we call Science Hill. This is where chemistry is located. Down at the main campus, old campus it's called, is one end. And this black outline is the outline of the West Campus. So it's almost the same size and shape. So we effectively doubled the size of our land area. And with these buildings, it provided the opportunity to increase the size of our science faculty at Yale. And so the West Campus has been used to create new institutes that are focused on themes of research, not departmental based. And each institute has been given 10 incremental faculty slots to hire new people. And so the Yale Energy Science Institute is one of those current seven institutes. I've been the director of the institute since it was started about 12 years ago. The West Campus has been growing. This is a little bit out of date. It's over 50 tenure track faculty now and about 18 different departments, including other functions as well. The museum collections and the School of Nursing are located on the West Campus. And in addition to the institutes, which are focused on research themes, we've been introducing instrumentation centers. We call these cores. And the ones that are relevant for our institute, we have a materials characterization core, we have an analytical chemistry core, we have a center for research computing, for high performance computing, and we have a clean room. And those are all used quite extensively by the faculty. And one of the things that's really special about this West Campus site is that, and these institutes, is that they're not based on one department. So in the United States, and I think that's probably true throughout the world to a large extent, disciplines are largely siloed, which means chemistry is in a chemistry building and the chemistry faculty talk to chemists. And the physicists are in a physics building and they talk to physicists, but they don't talk to each other very often because they're in separate buildings. And this creates barriers for interdisciplinary research. And I would argue that energy absolutely needs contributions from multiple disciplines to solve this problem. It's not a simple problem that only chemistry will solve or only physics will solve or only engineering. And so this is an opportunity to carry out interdisciplinary energy research under one roof. And I choose that. Under Barack Obama, Steve Chu was the Secretary of Energy, and he introduced new research programs, including what were by the Department of Energy called hubs, which were interdisciplinary programs. And he was hoping to emulate the Bell Labs environment. Bell Labs had this amazing group of researchers from many, many different disciplines, science and engineering, working in one space. And he wanted these hubs to be under one roof. It didn't really happen. The hubs that were funded were not under one roof. But we are in this institute. We have faculty from 6 different departments: chemistry, physics, MEMS, which is mechanical engineering and material science, CE, which is chemical and environmental engineering. This is Professor Kim's department, applied physics and electrical engineering. And we're all working in one open lab. And these are the current faculty. We have right now 14 principal investigators working in the institute. Many of us working on the energy production, solar energy conversion and storage. Myself and Bob Crabtree and Victor Batista. A number of people working on materials science, especially quantum materials. Also measurements, spectroscopy, and other methods, and device applications for devices. And one of the things that we really have emphasized is the interdisciplinary and overlapping areas. So for example, we have a very strong connection between theory and experimental groups, and the theory and experiment connection is really a critical one. And just to give you a little bit of an overview of what we do in the Energy Sciences Institute, these are some three of the major areas where we're doing research. One of them has to do with materials science. This, in fact, is a priority area for the future for Yale University as a whole. And we've been working with materials for battery applications, quantum materials, designing new materials, and particularly for solar energy applications, developing new photocatalytic materials. My group and others in the Institute work on catalysts for energy conversion. We'd like to take small molecules like carbon dioxide, water, dinitrogen, and turn them into liquid fuels such as alcohols, hydrocarbons, and so on, or ammonia, or gaseous fuels such as molecular hydrogen. And so we work on aspects of carbon dioxide capture and conversion, nitrogen reduction to ammonia, and my own area, water splitting chemistry. And as I mentioned, we have a very strong connection between collaborations between experimental and theory groups for solar fuels research. This is a table of contents graphic. We wrote a review article, Victor Batista and I, with case studies of how to effectively connect theory and experiment for solar energy research. And some of the areas where the theory is being developed, including machine learning methods for catalyst discovery, modeling of catalysts, and design of new materials. And I think in many of the cases, the theory and experiment go hand in hand, from planning the experiments in the beginning to analyzing the experimental results at the end. And this is kind of our picture here of what happened to the pointer there. Okay, and so with that as a, it'll be good, just before I go on, these are some of the new labs that we have. The West Campus, that was when it was owned by Bayer, has been mostly renovated. This is new renovation of the Energy Science Institute. We moved into this renovated space about 3 years ago, and this is where my labs are right here. This is what it looked like before we moved in, so brand new spaces. And we also have instrumentation centers. I mentioned the materials characterization core. We have a number of different instruments that we use for our research in that core facility. And one of the things we're very excited about is that we're having a new core facility that is projected to be open this fall for aberration-corrected electron microscopy, ACEM core, and we'll be installing an aberration-corrected TEM instrument in the next few months, and that will be a new core facility that is available for research. And I think we saw some pictures in Professor Kim's talk using this instrument, probably not done at Yale though, because we don't have that. And I'll show some too, which we had to go to other places, but now we'll be having to be able to do those right at Yale. Okay, so with that, I'd like to turn to the research that we're doing. And this is, I think, a sort of a segue to my own research. So my group researches in two areas. One is natural photosynthesis. Into storable chemical fuels. This is the only solar fuel process that's operating at a global scale right now. We do not have an industrial process for that. And we'd like to understand how what are the design principles in nature. So one half of my research group works on the biological processes of photosynthesis, particularly focused on the protein complex called photosystem II that does light-driven water splitting and oxidation. It produces the oxygen that we breathe. All of the oxygen, essentially all of the oxygen in the atmosphere was produced by photosynthesis. And with those design principles, we'd like to then use those principles to develop artificial processes to make solar fuels. And the idea would be to make an artificial leaf where we could shine light on it and store the energy of the solar photons in the form of chemical bonds. And this is the work that we're doing in the Energy Science Institute, and that is what I'll focus the rest of my talk on. I'm not going to talk about our biological photosynthesis today, but I'd be happy to discuss that with anyone if they're interested. And we do this work in collaboration. This is a group that has been working at the Energy Science Institute. We started up a collaboration actually before Yale purchased the West Campus, and that's one of the reasons we were the pioneers at the Energy Science Institute. So myself, Victor Batista, Bob Crabtree, and Charlie Schmittenmeyer teamed up about almost 20 years ago to try to develop catalysts attached to metal oxide materials such as titanium oxide for light-driven solar fuel production. And so Victor Batista, right here, is a computational chemist. Myself, I'm a biophysical chemist. Bob Crabtree is an inorganic chemist here, and Charlie Schmittenmeyer, an ultrafast spectroscopist, terahertz spectroscopist. Unfortunately, Charlie passed away a few years ago, so his research contribution has been fading away. His group is now completely finished up, and so we're continuing that kind of work in collaboration with others. But Victor, myself, and Bob are still working together at the Energy Science Institute on solar fuel project. So this is kind of the overall idea of what we're trying to do. We're trying to synthesize molecular catalysts that can do, in particular, water splitting. We're interested in the water oxidation part of that reaction because it's the most chemically challenging. It's often, in fact, it always is the kinetic bottleneck for overall water splitting. And it's difficult and challenging chemistry. So we've been working on catalyst design. Of course, we have to connect it to the surface of metal oxide semiconductor materials such as TiO2. And so we've been working on anchoring chemistry and then linkers and also dyes as for dye-sensitized water splitting. And I'll talk particularly on the development work that we've been doing on catalyst design and a little bit on the anchoring chemistry and then on light-driven water oxidation. And so the idea is that we would have a catalyst that would be where we would have a light-absorbing material, either a dye or a semiconductor, that absorbs light and injects electrons into the conduction band of the semiconductor. Those electrons could be transported to a cathode side where the reductive chemistry, hydrogen evolution would occur, and it would leave behind oxidized nucleons that would drive a water oxidation catalyst to do oxygen production from water. So that's the overall design, and the key thing for doing this is catalyst design. And we can do that in two ways. We can make molecular catalysts, these are referred to as homogeneous catalysts, or we can use materials that carry out heterogeneous catalysis. Both have pros and cons. So for example, in the case of homogeneous catalysts, we have the advantage that we can tune them. They have the possibility of using chemical synthesis for rational design. We can characterize their structures and mechanisms in solution, which provides opportunities for optimization. And often they're the highest efficiency for doing the catalysis. But the big disadvantage is their instability. And why is that? Well, this is maybe a reflection of that. So if we're interested in water oxidation, we have to break the OH bond of water, which has an energy of 119 kilocalories per mole. If we have an organic coordination complex, an organic ligand, that has either aromatic CH bonds or aliphatic CH bonds, these are the bond energies for aromatic or aliphatic CH bonds, and they're less than the bond energy of water. What does that mean? It means it's harder to oxidize water than it is to oxidize anything organic. And so if you make an organic coordination complex, the question is, can it be stable? And in fact, in solution, it's not, because if you have a catalyst that can freely dissolve in solution, it will diffuse to another and chew itself up. But it can be done, and biology tells us that it can be done because nature has designed a biological photochemical process to oxidize water in a protein. Everything in the protein is easier to oxidize than water, yet this system will do millions of turnovers and doesn't degrade because it oxidizes incorrectly the protein. And so it can be done. And how is that? Well, we can combine overcome the instability and create high efficiency by preventing the catalyst from diffusing. If we take a molecular catalyst and anchor it on a surface so that it can't move around, it can combine high stability and high efficiency. And I'll show you an example of that. Okay, so that's the idea. Just a little bit of background. So molecular catalyst for water oxidation is a big topic right now. The very first that was reported was this ruthenium complex reported by Tom Meyer in 1985. It's sometimes called the blue dimer. It has two ruthenium atoms linked by an oxygen and coordinated by these bipyridine groups. And this was the first molecular water oxidation catalyst. In 1999, that's 25 years ago, Bob Crabtree and I reported this manganese complex. I should point out, nature uses manganese as the catalyst, and so we were very much interested in using manganese. And we made this manganese complex, which is somewhat similar in that it has two metals with oxygens bridging it, and we used a coordinating terpyridine ligand. Interestingly, in 1999, these were the only two types of molecular water oxidation catalysts known. Now, if you open up an issue of the Journal of American Chemical Society, almost every issue has a new water oxidation catalyst. There's just thousands of them now that have been reported over the last 25 years. Interestingly, though, this remains the most active manganese-based water oxidation catalyst, and this is what Bob Crabtree calls the principle of initial optimization. So we have not known has yet made a manganese catalyst that's better than this manganese terpyridine complex, except biology and nature. Now, what about the design principles? So let me take a little section of the periodic table. So I would argue that biology had the choice of any of the first row metals. Biology has to use abundant elements in order to grow, and the first row elements are the abundant transition ions, and it chose manganese. And I would argue that manganese is the best metal for catalyzing water oxidation of the first row metals. Now, in inorganic chemistry, we have a principle called the diagonal rule. Some of you in inorganic chemistry might be familiar. If you want to choose the element in the second row that has the most similar chemical properties as the first row element, you go down one row and over one, and that's ruthenium. The overwhelming number of water oxidation catalysts that we have to this date are based on ruthenium. And if you go down one more and over, it's iridium. Now, it's interesting because many decades ago, it was reported that of the metal oxides, the best heterogeneous catalyst for water oxidation is iridium oxide, and that's been known for many decades. But only recently were molecular iridium complexes reported. And so although iridium is not manganese, we continue to work on manganese. We've been very successful in developing iridium-based water oxidation catalysts, and that's what I'd like to tell you a little bit about today. And that was inspired by this work from Stefan Bernhard, was published in 2008. So that was not just yesterday, but it was relatively recently, 17 or 16 years ago. He reported this iridium phenylpyridine complex as a water oxidation catalyst, and that got us interested in molecular iridium catalysts. But in order to make an effective catalyst, you need to have an oxidation-resistant ligand. And we need to have a ligand that also is not only oxidation resistant, but it promotes high oxidation states, because you need to have high oxidation states to activate water for oxygen production. And we've looked at a lot of different ones. I'm going to tell you about the winner. The winner is this ligand right here. It's a pyridine alkoxide. Here's a pyridine group, has coordinating nitrogen, alcohol group, which has the possibility of deprotonating to form an anionic alkoxide, which very strongly stabilizes high oxidation states of metals. In fact, we've used this ligand to produce previously unprecedented oxidation states of palladium, manganese, and iridium because of the ability to stabilize high oxidation states. So it does that by being a strong electron donor. It has good chelating properties, so it binds as a rigid chelating ligand. Its solubility is good, and it's oxidation resistant. And so this has been really the ligand that has enabled some really successful molecular water oxidation catalysts. And here's the one that here's how we've made it. Starting from a precursor, which is inactive, this is has this pyridine alkoxide ligand, pialka we call it, bound to iridium, and it has a sacrificial coordinating group, this pentamethyl cyclopentadiene group. And we can either by chemical oxidation or electrochemical oxidation form this iridium dimer, which is an incredibly good water oxidation catalyst. And we call it our blue solution species. And this is just showing this complex, if we turn on a 1.6 volt, doesn't produce any oxygen, but the blue solution produces oxygen at a very high rate. And this blue solution is an activation from this initial precursor. The chelating group has retained the placeholder. This methyl cyclopentadienyl is oxidatively lost. It doesn't make any iridium oxide nanoparticles. We measure that by dynamic light scattering. It's stable over time, and it's very active for water oxidation. So here's after activation, we make a solution. We can keep that on the bench top for months. It's perfectly stable. And we can also characterize its structure. We haven't been successful to crystallize and determine the crystal structure, but we can use spectroscopy, X-ray absorption spectroscopy, and XAPS, and high-energy X-ray scattering, together with theoretical modeling to predict that it's a dinuclear iridium complex with a single oxygen bridge with coordinating waters and pyridine oxide ligand to it. And it is a very good catalyst in solution, but as I mentioned, we want to, for stability reasons, put it onto a surface, and this would be referred to as a heterogenized homogeneous catalyst. So homogeneous means molecular, heterogenized means a material, and this is a molecular catalyst that's anchored on the surface of a metal oxide. And it turns out we don't need to do any fancy chemistry to anchor it. It spontaneously absorbs onto metal oxide. So here's our blue solution we make by a chemical or electrochemical activation of this pre-catalyst. We can make a mesoporous film of different metal oxides and just soak the film in this solution, and the blue solution catalyst, this iridium catalyst, binds very tightly to a variety of metal oxides: titanium oxide, tin oxide, tungsten oxide, iron oxide. And it's really strongly bound. We tried to find conditions that would remove it from titanium oxide, and the only conditions that would remove it were conditions that dissolve titanium oxide. So it's basically integrated onto the surface oxide lattice, we think, through titanium, oxygen, iridium bonds that are very stable. And that allows a very convenient form for electrochemical and photoelectrochemical study. So one of the ways that we can study this is by using a conducting metal oxide. So ITO, nano-ITO is a mesoporous indium doped tin oxide. It is electrically conducting, and so we can absorb this iridium catalyst on the surface and then do cyclic voltammetry of the catalyst. And just to take you through this blue trace here, we see a oxidation, reversible oxidation, which is an iridium 3 to 4 oxidation, followed by onset of catalysis, which shows this jump in current that happens essentially right at the thermodynamic potential. Now, what does that mean? So normally when you do catalysis of water oxidation, there's a very large overpotential, and it's the voltage that you require above the thermodynamic voltage to do the reaction to make it go fast enough. Typical overpotentials are on the order of 400 millivolts or so, and this, we see an onset within 15 millivolts. This is the very best that has been achieved, and it's completely stable. And so we can characterize the surface by using X-ray photoelectron spectroscopy. This is after 100,000 turnovers, and we can study the iridium, the nitrogen, and the carbon chemical nature on the surface, and we see that they're identical after 100,000 turnovers. There's no measurable degradation. Staff Sheehan, the student who did this, actually carried out an electrochemical cell for a month, which he calculated had on the order of more than 5 million turnovers, and it was still unchanged. So this is completely stable, as opposed to the behavior you see for molecular catalysts. When you let them diffuse in solution, there are none, including this, that are stable for very long. So this is a design now principle, I think, that allows us to go forward with optimizing catalysis with the molecular catalyst and putting on a surface that impart stability. And I should point out, Staff Sheehan has gone on to start up a company. I didn't make a slide of it, but he started up a company called Air Company, which is I believe, the only company making solar fuels and making a profit. And the reason for that is that they're not burning the solar fuels. They're making ethanol from carbon dioxide electrochemically, and they're selling the ethanol as vodka at $100 a liter. And so he's actually making a profit, and he's gotten a lot of awards, including Forbes 30 Under 30, and he recently won the NASA Challenge Prize for carbon dioxide conversion, which was NASA wants to convert carbon dioxide into food for a Mars mission, and so Staff in his company won that competition. So this is making use of the same kind of design principles we've discovered in the research. Of course, if we want to do solar fuels, we need to drive this by light. And the idea then is we're going to have a catalyst that's anchored on a metal oxide that is initiated by light to do water oxidation, convert water into molecular oxygen, releasing electrons, which can be utilized for hydrogen production to give overall water splitting to produce oxygen and hydrogen. And here's a picture of a laboratory apparatus using an H cell where we have a little mesoporous surface with the blue catalyst on that, you can see here, and hydrogen being produced on the cathode in the other side. We've done a lot of work with synthetic dyes, and I'm not going to talk about that. I'm going to talk about using hematite. So hematite is iron oxide. Rust, you know rust is colored, and that's because it absorbs visible light. And so we don't need a dye if we want to use hematite. The problem with hematite, however, is that its photochemical activity is not that good. And so this is a plot of photocurrent in terms of J milliamps per square centimeter versus applied potential voltage. And you can see there's a turn on somewhere around a volt for photocurrent. If we put our catalyst on the surface, this iridium blue catalyst, we can see it shifts by several hundred millivolts to lower voltage. So we're significantly improving the photocatalytic performance. And we've been able to use this to make complete solar water splitting cells. And this is a system where we, within a single chamber, utilize a iridium catalyst on the photoanode and an amorphous silicon on a photoanode. And this is the idea. We have a photoanode that absorbs the blue and the shorter wavelength range of the visible photons. The longer wavelength photons pass through and drive the photocathode. And we get overall water splitting with 100% Faraday efficiency and no applied voltage. So it's just a complete water splitting cell. And moreover, it works under acidic conditions, which is almost exceptional because if you want to do water oxidation, of course, it's going to generate protons from the oxidation of water. It's going to drive itself to be acidic. And so working under acidic conditions has been a real aim for development of this. And so this system does that very effectively. Now, how is it working? And so we're putting this catalyst on the surface, and we're showing an image of the surface using a aberration-corrected transmission electron microscope. And this is a facet of hematite, iron oxide, and we're seeing individual atoms of iron on the surface. But in various locations, we see two brighter spots here, 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 and here. And those brighter spots we interpret as being the two iridium atoms. And you can see if we scan across from here to here, the intensity, we see roughly equivalent intensity. Then we see two higher intensity peaks and back to the iron intensity. And these two higher intensity peaks overlay exactly with the position of iron. And so what we think is that this iridium dimer is laying down side on into a position that's immediately above an iron atom on both positions. And interestingly, this is a site where there are 3 oxygens on the surface that are in a position to coordinate the iridium, and they're spaced exactly at a separation of the iridium dimer. So we think the iridium dimer is laying down side on to produce a side-on bound catalyst, and it's still catalytically active on the surface. And this just shows some photocurrents where we take the hematite by itself. We can put nanoparticles. As I mentioned, iridium oxide nanoparticles is the best heterogeneous catalyst based on oxide nanoparticles, and it slightly improves. We can put a single atom catalyst, and it slightly improves better, but the dimer is much better. And I think there's two reasons for this. One is this is a 4-electron reaction needing, and two metals can help facilitate that. I'll show in a minute the difference between single atom catalysts and this DHC or dual heterogenized catalyst is stability as well. And the dual atom catalyst is much more stable. And interesting aspect is we also can anchor this onto tungsten oxide. When we image the surface, I don't have a picture here, we only see single spots. And we initially thought maybe it's breaking apart. But in fact, it's not. It's just laying on, it's binding side on. And we can confirm that by looking at drifts. It's a diffuse reflectance infrared spectroscopy. And we see splitting of the peaks reflecting two inequivalent environments for the binding of carbon monoxide onto the catalyst. And that's well agreeing with simulations. And so we modeled this as a side-on binding mode. And again, it's improving the catalysis. So this is interesting. And we think the reason that it's binding side-on is that the lattice spacing of tungsten is larger than the lattice spacing of iron oxide. So there's that sites are too far apart to lay down side-on. So that forces them to lay down end-on. You might ask about the mechanism. So this is a computational mechanism by a postdoc from Victor Batista's group, Kayang, and he computationally modeled this iridium catalyst on the surface of hematite. And based on the computational model, we proposed a mechanism that involves sequentially oxidizing the iridium ions up to a high oxidation state of iridium 5, which then enables water to attack through a what's referred to as a water nucleophilic mechanism. The water forms an attack to form an O bond, which then with the fourth oxidation is releasing oxygen. So that is a computational model. Of course, we're interested in understanding the mechanism because it allows us to understand better the chemistry and maybe optimize the design as well. Okay, so that's what we've been working on. And let me just sort of wrap up with the conclusions. We proceeded by initially designing and optimizing molecular catalysts, and that's an area that we're continuing to work. With a optimized molecular catalyst, we can characterize its structure and function in solution. And then we can anchor it to a semiconductor material for stability and chemistry, and the heterogenized catalyst can carry out the chemistry with high efficiency and stability. Now, I want to just mention one last thing. These iridium catalysts aren't only effective water oxidation catalysts, but we've recently been able to show that this iridium dimer can carry out the preferential oxidation of carbon monoxide in the presence of excess hydrogen. This is called PROX. This is a challenge because hydrogen right now is made by steam reforming of fossil fuels. And that mechanism or process produces carbon monoxide as a contaminant of the hydrogen. But using hydrogen as a fuel in a fuel cell, the carbon monoxide will poison the fuel cell. So you have to get rid of the carbon monoxide. And that's a difficult challenge. And what we found was that this dinuclear iridium catalyst adsorbed on now a non-conducting oxide, cerium oxide, with 40% hydrogen, 1% oxygen, and 1% carbon monoxide. We can get very high efficiency. It varies with temperature. At the optimum temperature, we get almost 100% conversion of carbon monoxide into carbon dioxide without losing the hydrogen. So that's a really challenging reaction because it's easier in general to oxidize hydrogen than carbon monoxide. So that's another chemistry that we've been working on. And let me just end by thanking all of the people who've done this. These are the names of students and postdocs in my group that have worked on this. We collaborate with Victor Batista on computation, our solar group, I mentioned Victor Batista, Bob Crabtree, and Charlie Schmidtmeyer, and some of the others who we've collaborated with on materials and spectroscopy over the years. And of course, the Yale and the energy sciences have been absolutely key to be able to provide the environment for carrying out this research. And with that, I'd like to thank you for your attention. I'd be happy to answer any questions that you might have.
Thank you for the great presentation. By the way, I love the buildings at West Campus. So, if anyone have questions from the floor, just feel free to ask me.
I think there's a microphone.
Thank you for the great talk. I have one question. I wonder, actually, iridium is noble metal. So I think the performance of your diatomic iridium, the molecular catalyst looks really good in acidic medium. But have you ever think about the economical benefit compared to other transition metal catalysts for the
Yeah.
oxygen?
Yeah, that's a great question. And obviously, iridium, the complaint I get all the time is iridium is one of the least abundant elements. I didn't make a slide, but we have a slide similar to the one that Professor Kim showed about the cost of these individual catalysts on the surface. So even though iridium is pretty expensive, it's not expensive to put single catalytic sites on the surface of material. You have very high efficiency of use of sites. 100% of the sites are active. And you'll notice that when the TEM picture I showed, we had a very low coverage of the surface. We're not covering the whole surface. We have maybe only 10% coverage, and we're still getting significant improvement. So I do think iridium is not necessarily too scarce to be able to do this work. But we're very much interested in trying to find more earth-abundant elements, particularly first-row elements. The real challenge, and this is a challenge facing the entire field, is that the bond energies of ligands to first-row elements are much weaker. And so they rearrange much more readily. And we have not been successful to find a catalyst that's very stable based on a first-row system. And that's going to be a challenge to come up with design principles and design approaches that will give stability. But we're very much interested in other metals, and maybe even a bimetallic system with iridium with another metal might also be a possibility.
Thank you.
I have one question. So blue solution is based on the iridium catalyst, right?
Yeah.
So does it have ability to take CO2 uptake or CO2?
We've looked a little bit, but so CO2 conversion is a reductive reaction.
Right.
And the reactions we're working on are oxidative reactions. So to do reductive chemistry, we have to go to lower oxidation states. There are some possibilities. We have actually shown that you can do some reductive catalysis with iridium, but it's not that good. And so we haven't really found good applications for it yet. And I did show the oxidation of hydrogen doesn't occur. That's one of the reasons is the iridium hydride bonds in these oxidation states are just not favorable. And those are probably important to do CO2 reduction. Most of the mechanisms involve metal hydride reacting with CO2 to form some kind of CH bond. So I don't think this catalyst that we're working on is the right choice for carbon dioxide conversion. But there are others that have been shown. And one of my colleagues, Hailiang Wang, who's in the Energy Science Institute, is a phenomenal system for converting carbon dioxide into alcohols and using cobalt catalysts. And so
Thank you. Any further questions? No. Let's wrap up this session. So please give him a big applause again. This is the end of first two scientific sessions. We have now 20-minute break. So we will be back on 4:20. Thank you. Now we're gonna have 3 sessions with speakers from Korea University. Now it's Korea time, so we don't have any Q&A session. After 3 sessions, we're gonna have wrap-up discussion. Let me introduce first speaker, Professor Seung-Kwan Hong. He is a professor at Civil and Environmental Engineering.
The first thing that I want to say is I welcome you again, the 2 professors from Gary and Jae-Won Kim from Yale University. It is my great pleasure to have you at Korea University and have this, engaging, the discussion regarding water and energy, climate technology. And also, I like to move around when I'm talking. So, what I'd like to do today is I'm going to talk about the 2 things. The first, I'd like to share my experience with the seawater desalination project, which is very important now these days in order to secure water supply for more industry as well as the human society against climate change. And then the second part, which is a main topic of today's my talk, regarding securing water resources for high-tech industry in Korea. As you know, the semiconductor industry is a big giant the industry in Korea, and very important to have sufficient water for ultra pure water production, which is very critical for manufacturing semiconductor in Korea. And with that, I'd like to start my talk here. So securing industrial water by using alternative water resources. And this data is taken from GWI, the latest data. When you look at loss that you have from disaster associated with climate change, the 69% of damage is water related, and including storm, flooding, drought, wildfire even, and all those things indicating that securing water supply for the future against climate change is very critical. And especially, Professor Kim also talked about, making American industry more competent in the future. The securing water resources is very important. And based on this, GWI water data, capital employed in delivering corporate water security will grow from $500 billion in 2024 to $32,000 billion in 2034. So it is very important to secure the water resources by using alternative water resources. And so that's why in water sectors, we can see this trend. As you see from this slide, the water reuse and seawater desalination, those are the 2 alternative water resources that we can utilize to secure water supply for industrial purpose. And this diagram shows the last 20 years, seawater desalination and also water reuse have been increasing every single years. So now we are expecting this trend will more apparent in the future. And one of the issues when you try to utilize low quality source water is you need to apply more sophisticated and the multiple barrier of treatment processes. When you do that, what's going to happen is you end up using more energy in producing water from low quality source water. As you see from this diagram here, when you try to do water reuse, then the energy cost to produce 1 cubic meter of water produced is ranging from 1.0 to 2.5 kilowatt hours. Seawater desalination, even we are using more energy as expected, maybe 2.6 to 8.5 kilowatt hour, depending on what kind of process that you're going to use. So critical issue securing the water resources for industrial purpose is energy here. So what we need to do is we need to develop technology that we can reduce energy consumption further. And Ministry of Environment and Korean government try to invest money. Try to support R&D activity in the seawater desalination to improve energy efficiency in seawater desalination plant. And that project started in 2016 and then ended in 2022 with a budget of $31 million US. So this is a huge project that Korean government funded. Fortunately, I was appointed as a research director of entire this project, and then Korea University is hosting, institution for this entire project. We have many, participants, including LG Chem, which is making, outer membrane in this project, and Samsung Engineering developing pre-treatment processes, and also Daewoo, number 3 construction company in Korea. They are actually constructing and design and constructing pilot plant, and K-Water, the number 1 water service company in Korea, they are operating this pilot plant. We are working with a master company, and also we have a subcontract with Khalifa University for doing research. And so this project is the first project, R&D project that Korean government is funding, and to go abroad, and then we are working with, as you see, from United Arab Emirates. And the first thing that we need to do to reduce energy in seawater desalination is we need to find out the causes of, using or increasing energy consumption in seawater desalination. We collected 75 data sets from large-scale seawater desalination plants all over the world, and then these are some of the results here regarding the Arabian Gulf area. And the first reason why we are using, large energy consumption and large energy in this process is the feed water salinity is pretty high. So in order to overcome the high salinity in this area, ranging from 45,000 to like 53,000 in this area, very high salinity in Arabian Gulf, and high pressure operation is needed. And also number 2, energy intensive pretreatment for algal or oily removals. And dissolved air flotation is normally applied, and this dissolved air flotation requires a lot of energy for air bubbling. The last thing is the stricter permeate water quality. In this area, you need to reduce the salinity all the way down to 200 or 300 TDS. And that means you need to have second pass RO in addition to seawater RO desalination process. So that ends up, we have huge consumption of energy in seawater desalination. So based on those causes, we developed strategies reducing energy use further. And this is what we did in this project. Number 1, technical advancement number 1 is we need to develop low energy RO system using world-based RO membrane. So you gotta have best performing RO membrane in the world. Technical advancement number 2 is energy conserving algae response pretreatment. So instead of DAF, dissolved air flotation process, we have to have different type of energy conserving pretreatment processes. Technological number 3, low energy future technology for replacing second pass RO. And what we did was electrochemical processes, and such as CDI, and those technologies were developed in this project to reduce energy further. And combining all these, three axes of development, we designed and constructed pilot plant of 1,000 cubic meter per day. So when you're talking about 1,000 cubic meter per day, seawater desalination plant, the pretreatment process, we are designing 2,400 cubic meter per day pretreatment processes. So this is not just small size of pilot plant. This is actual seawater desalination plant. And then we demonstrate this one at the design of 100,000 cubic meter per day with a goal of energy consumption at 3.3 kilowatt hour of cubic meter of water produced. So at that time, that was a very ambitious goal of energy consumption, which we believe that under this condition, the world best energy efficiency. And because of COVID-19, we experienced very difficult period of constructing and designing and also constructing this pilot plant. However, we were able to finish this pilot plant in 2021. And then we operate this one for 1 year. And then here's some of the main outcome here. LG Chem developed low energy SWRO membrane modules, as you see from this table, and while maintaining flow rate of 9,900 GPD, salt rejection is maintained at the highest level. That is very difficult to do. When you increase productivity, then you actually compromise salt rejection. However, LG membrane was developed to achieve this goal, high productivity with reasonable world best salt rejection. By having this membrane in your systems, we were able to achieve the world best energy efficiency or reduce energy further. And here's a final result. As you can see from those tables right here, we were able to achieve specific energy consumption at the rate of 3.0 under the condition of TDS level below 300 or 200. And this one has been published in Desalination, as well as the master company made reports for this project, indicating all parameters were found to meet the guaranteed values, resulting in the successful completion of the Korea Research Pilot Desalination project. I share this, the experience, and this is a way to go. We are still hungry to reduce energy further by having various technology. In this project, we tried, many different things, and then published many, numerous papers, for the futures. So including the fold osmosis membrane or the electrochemical processes. And so still we have a long way to go, and then this effort should be continued. Okay. And then now I'm going to talk about ultra pure water production, which is the main topic of my talk today. And Samsung and also SK Hynix, those are the two major semiconductor manufacturing the company in Korea. Actually, they are the number 1 and number 2 in terms of memory chips in the world. And in this, manufacturing process, UPW, ultra pure water consumption is very, very high. We're talking about not just small amount of water. We're talking about, the 800,000 tons per day in order to support, one, factory. That is the amount of water that city of Daegu is using per day. And so this huge amount of water are needed in order to, increase the capacity of semiconductor manufacturing in Korea. So this is a significant problem for Korea at this moment. Samsung or SK Hynix, they try to expand in order to compete in the market with company like a TSMC in Taiwan. Water and energy supply, those are big problems, very critical. And one of the solution is not only not only rely on seawater desalination, but also we try to do water reuse, especially the wastewater from semiconductor manufacturing process. Recently, review paper has been published and then indicating that the pollutants from semiconductor fabrication process should be controlled, completely in this wastewater treatment processes. So what we need to do right now is, in order to ensure a stable supply of ultra-pure water, integrated water resources management is crucial in response to climate change. So climate change will give us problem, water shortage, seasonally and regionally. However, semiconductor industry cannot tolerate this fluctuation in water supply. And that's why we have to really focus on, integrated approach to supply water for semiconductor industry stably. And this is a typical UPW production. And you see, many, multiple barrier of treatment processes or schemes are applied to produce ultra-pure water. And pre-treatment stages and the makeup stage and polishing stage, each stage has like 7 to 8 different processes in cities. And I'm not going to talk about all of this UPW production. And let's focus on organic control. Those organic pollutants are used in semiconductor manufacturing process. So if we try to use semiconductor wastewater, then those chemicals will be present in wastewater. And they will affect this ultra-pure water production processes. So some of them, you can see, some of them can pass through RO, reverse osmosis membrane, as we discussed in the seawater desalination, and also TOC UV. The 185 nanometer wavelength is used to degrade organic matters. And when you look at this, makeup stage and polishing stage, RO and UV, those are the two processes to degrade or to remove organics in UPW production. You can start to worry about what's going to happen to low molecular weight organic matters, such as methanol, ethanol, and urea or DMSO, and also the IPA, TIMA, all those things, the chemicals that are used in semiconductor industry. They can be present in the wastewater. They can survive through wastewater treatment schemes. And then that's going to affect UPW productions. So what we did in our lab, we tried to verify the fate of those low organic matter molecules. We conducted experiment with RO. For example, here we got the membrane from major companies like Toray, LG, Chem, and also Dow Chemicals. And as you see, the methanol and ethanol urea, those are rejected only, less than 60%. And IPA, DMSO, TIMA, they are also, rejected at the level of 80 to 90%. Not good enough. Okay? So RO is designed to reduce salinity, TDS level of your water, but organic matter, as far as low molecular weight organic matters are concerned, they are not effectively removed by RO process. So what we need to do? We need to also TOC UV. Vacuum UV should be applied to degrade these organic matters further. They are working or not, here's the result. Methanol, ethanol, IPA, DMSO, as you see, at 185 nanometer, and then increasing intensity, then we were able to actually degrade those those organic matters. However, TIMA and urea, particularly, they are not degraded by the vacuum UV in this UPW process. So urea is a very stable compound and low molecular weight, and they can survive through RO and then vacuum UV processes. So that's why now these days in Korea, we try to develop the urea treatment processes in many ways. I think the Professor Kim also interested in this process and then making a proposal with the K-water. And these are some of the urea removal technology that I can come up with. And adsorption process, membrane separation, of course, biological removal, thermal hydrolysis, enzyme hydrolysis, and also wet air oxidation, UV-based AOP, advanced oxidation process, and also electrochemical oxidations. All these processes have pros and cons as listed here. And however, and up to this point, no, effective, also real scale urea removal technology have been developed. Our lab, also Professor Kim's lab, I think we tried to develop, the advanced oxidation process to enhance the urea removal in semiconductor wastewater treatment processes. Because of a time limit that I have, I do have some of the data that I can share with you, but we are making some progress and then also advancement. Hopefully, we can prove that we have effective controllable organic matter in the future in UPW production. With that, thank you for your listening.
Thank you for the nice presentation. I know you guys have tons of questions, but due to the time limit, we will get the questions after 3 sessions. So let's move on to the next presentation. Let me introduce Professor Junong No. Please welcome him. He's the professor at Civil and Environmental Engineering.
Thank you, Professor Won, for kind introduction. I'm Junong No in Korea University. I'm so appreciate Professor Hong for giving me this opportunity to speak today. Actually, I'm so happy to introduce the highlight perovskite solar cells for you and to share our recent achievement is for perovskite solar cells. And I believe the perovskite solar cell is very good, innovative climate technologies for the future. Okay, so I'm prepared that this first page is from the roadmaps by the IEA, the net zero roadmap. And you can see it here is the emission change over the time by mitigation of measures of the carbon dioxide, net zero scenarios. You can see here there are many kind of those technologies for those mitigating carbon dioxide emissions. And as you can see here, so there are the wind and the solar PV. Solar PV is, will play a very important role in the futures. Okay, so this is a roadmap to net zero by 2050s. So there are strategies to obtain the net zero. So I just focus on the final target. You can see here the final target. Actually, includes the others, the roadmaps from international renewable energy agencies. You can see here that there are 2 roadmaps had a very similar target. Actually, I like to show you here the share of the electricity in the final energy consumption should be 50%. And you can see here renewable energies share in the power generations around 90%. 90% is to be generated by renewable resource. It's very important. So I can say is that summarize this target is electrification with the renewables. Okay, so how to produce renewable electricity? They also give you also roadmaps here, low emission electricity generation capacities. You can see here the solar PVs have to generate 60% electricity by 2050s. So it's very important solar PVs technologies. So I think we have to find new technology to harvest the sunlight anywhere across the various sectors, not just the utilities. So for example, it's the urban system and the building infrastructures or other applications is important to harvest the solar energies. So, okay, so we look at the solar cells, that's the photovoltaics. This is the conventional, the solar cells actually has a requirement is for commercialized high efficiency, long-term stability, and low cost. That is conventional golden triangles for solar cell. But how about the future photovoltaics? As I mentioned, it's very important to apply the various sectors for the solar cells. So we can also need to lightweight and flexibility and visible transparency and novel form factors that required for the future for the photovoltaics. And also the efficiency actually is that we also requires the ultra high efficiency exceeding 30% or 35%, and what lowers the cost is also required for the future. Okay, so let's look at the detail of the solar cells. This slide I just show you is the principle of solar cell. The solar cell is the most efficient way for directly converting solar energies into the electrical energies. And you notice that it's very important photons. The sunlight generates electron holes in the light absorbing material or semiconductors. For example, crystalline silicons, these vapors absorb the light and generate electron hole pair. And the electrons and hole is collected by external circuit and generate electrical powers. So the most important thing in the solar cell is how to design the light absorbing semiconductor materials. So, okay, so there are so many kind of those semiconductor and light absorbing materials. Here's, you know, so there are very famous semiconductors, silicons, actually the first group semiconductors, and there are also gallium arsenide, 35 semiconductors. You can also, there are 2,6 semiconductors, for example, cadmium telluride. And you know the silicon and gallium arsenide is based on the single crystals. If you fabricate the silicon solar cells, you have to grow on the single crystal vapors. You know, so we need this very high temperature, so 1,500 degrees Celsius to grow the silicon vapors. And how about the gallium arsenide? You know, so, if you make this device for gallium arsenide, you need this single crystal gallium arsenide substrate, and then every single layer is to be grown by epitaxially. So we need a very high temperature and vacuum process. So the single crystals has a high processing complexities. This is problems. And how about the polycrystal cadmium telluride CIGS solar cells? This kind of solar cell also is deposited by vacuum equipment. So we need the vacuum deposition at the high temperatures. Actually, so I think that so the conventional solar cell is not good for future photovoltaics. So many people are focused on the emerging PV, emerging photovoltaics. Actually, the emerging photovoltaics is based on the printing process. For the printing process offers great opportunity for mass productions, low-cost mass production features, like the printing newspapers. So, but in order it is important to printing the silicon or the CIGS. So many people focus on the novel materials for solution process. For example, dye molecules or organic semiconductors is a great candidate for printing photovoltaics, but this kind of materials suffer from low efficiency, the solar cells. But okay, today I like to focus on the halide perovskite. The halide perovskite, these materials enable to achieve the high efficiencies around 26%. Okay. So I like to show you this famous NREL's efficiency chart. You can see here they recorded the best certified efficiencies of the solar cells. There are so many kind of the solar cell type, and we mainly focus on the emerging PV. Here's this red line. When you return to the 10 years ago, we, as you can see here, the emerging PV is located at the bottom of this chart. That means that the efficiency is very low compared to their potentials for the printing the solar cells. But this time, the highlight perovskite actually is make the red line go to the silicons. So I will get to the detail here. You can see here, perovskite solar cells emerged the 14% here. And then you can see it's truly remarkable increase of the efficiencies here. And this time the efficiency is a single junction 26% is comparable to silicon. And you notice that Korean groups mainly contribute to the improve the efficiency. You know, they are the CRIT, Korea Research Institute of Chemical Technologies. I worked in the CRIT at the time, and we mainly focus on make the high quality the perovskite layers, and then I moved to the from CRIT to Korea University 2017, and then we also focus on the improve the efficiency of our labs. So our labs also recorded a world record efficiency at the time, and you know, there are the Chinese groups actually these times has also world record efficiencies, but our labs also continue to develop the high efficiency of perovskite solar cell. Okay, so how to achieve the perovskite solar cell high efficiencies? You can see here, perovskite, these names from the crystal structures. There is ABX3, that is the formula of the perovskite materials. At the time, it has a perovskite crystal structures, and we use the metal ammonium or formamidinium cations and lead halide ions. So it's very easy to, if you dissolve the metal ammonium iodide, lead iodide into the polar solvent, and then you can just vaporize the solvent, you can obtain high quality crystal. So this crystal has a very good optoelectrical properties. It is very it is suitable for the high performance for solar cells. So the perovskite solar cells is possible to high efficiency, low cost, the printables, flexible solar cells. So I just show you how easy it is to make crystal perovskite materials. You just mix the powder lead iodide and metal iodide, and then just mix. You can obtain the black powders in the room temperatures. You can also obtain the single crystal perovskite materials at the room temperatures using solution process. And this crystal is the comparable for the crystal silicon. As you can see here, this material has a very low the trap densities is comparable for the silicon. So the perovskite solar cells has selected is the top 10 breakthroughs, the science and the World Economic Forum, and this time the 5,000 papers related to the perovskite solar cells annually is reported. And in early stage of the perovskite solar cell research, so we mainly contribute to the improved efficiencies. So we developed the architecture of the perovskite solar cells, and then we tried to do the film formation process. We firstly make the compact perovskite layers at the first time by the solution process, and we design the materials, the highlight materials, and we can also design the surface engineering. So this technology is very important because these technologies continue to be employed for making the high efficiency perovskite solar cell in this time. And okay, so I just briefly introduced our research topics to our lab. And our labs also mainly focus on the efficiency, high efficiency for the perovskite solar cells. and then long-term stabilities. And can also focus on the various applications of the perovskite solar cells. Can also focus on the high efficient the tandem structures. Okay, so, I'd like to show you briefly the overviews of the top interest topics. For example, so here, we mainly focus on the electrical design of the perovskite solar cells. You notice it's very important to electrical design the device, the solar cell device. So we try to make the perovskite junctions. For example, here, so we make the narrow band gap halide materials and wide band gap halide materials. You can design the junction perovskite. And so we try to control those the electrical field is our diffusion region into the perovskite solar cell. And also, so we focus on the optical design. Actually, we mainly focus on the photon recycling. Actually, so universal gallium arsenide solar cell is the best device for single junction solar cells. The gallium arsenide already reached to the 30%, and the gallium arsenide mainly maximize the photon recycling into the light absorbing layers. So we try to mimic these approaches in the perovskite solar cells. So we maximize the largest combinations of the perovskite device, and then so you can try to improve the electroluminescence quantum yield in the perovskite device, so can obtain the 26% in this time. Okay, you can also focus on the oxide semiconductors. You notice that actually the perovskite solar cells include the organic layer, organic component. So the organic component is not good for the stabilities. The inorganic material is more robust than organic materials. So we are mainly focused on the oxide semiconductors. We would like to replace the organic materials by the oxide semiconductors. So, okay. This is the last pages. You notice that the perovskite solar cells already achieved 26% of single junctions. And you can see here, perovskite tandem solar cells achieved 29%. And you notice the perovskite silicon tandems around 34% is achieved. And for the silicon companies actually pay attention for the silicon perovskite tandems. I think this efficiency is continue to improve. So the perovskite solar cell has to be technical innovation in the solar cell industry for the futures. But there are some problems on stability and yields mass productions. Actually, so we continue to study to improve the stability and mass production of perovskite solar cells. I hope the perovskite solar cell will be the main players in next generation solar cell for achieving net zero target. Okay, so thanks to our lab members and collaborators and independent agencies in Korea. Thank you very much.
Thank you for the presentation. Let's move on to the final session. We have invited Professor Sang-hyuk Lim. Please welcome. He is now the professor at Department of Chemical Engineering.
Yeah, thank you. And actually, I saw all of your guys in the research proposal. So today we explained what I am doing. So I think this will be start of the good collaboration. Okay. Actually, the Professor No already explained the perovskite solar cell in detail. So I briefly introduced what I am doing now. So I just narrowed down to the focus on the inorganic perovskite solar cell to this time. So now I am focusing on the perovskite material. Actually, my major is the polymer. And also I am studying that the synthesize many the tiny nanoparticles, including polymers and metal and semiconducting material, and metal oxide. And then I'm finding to the application of the nanomaterials. So about 12 or 13 years ago, actually Professor No and I started to study the perovskite material in Crete. Okay. So at that time, we started to study the solar cell using the perovskite material. So we are still extending to the application of the perovskite solar cell, including the transparent solar cell and stretchable the solar cell and flexible and the module, including the tandem solar cell. And also the perovskite material is good to the new light emitter. So when we make the tiny perovskite nanocrystal, such as the quantum dot, then we can make that bright the emitter. So we can applicable the perovskite quantum dot to the light emitting diode or the color conversion material like the so-called the phosphor material. And also when we make the single crystal of the perovskite material, then we can use that to the hologram system because we can store that information of the electrical signal or the light signal as well. So we can make the hologram system using the photoreflective material. And also, similarly, if we actually the perovskite material is the ferroelectric materials, then we can make that the resistible random access memory, such as the ferroelectric material like the hafnium oxide or the barium, strontium, titanate. So, and also the perovskite material case, as the professor already explained that the structure, so we can control that the conductivity of the electrons, and also we can control that the phonon scattering. So then we can apply the perovskite material to make the good thermoelectric material as well. And also the perovskite material had that the lead or that the tin, so which had that high G number. So they have many abundant electrons, so they can fully absorb that X-ray or the gamma ray or the beta ray as well. So we can apply that perovskite material to photodetector or the cosmic ray detector. So neutron detector or X-ray or gamma ray or the beta ray detector as well. So today we just talk about the inorganic perovskite solar cell. And also we are actually this government do not want to study that solar cell. so I study the photo battery. So by integrating the solar cell and the battery system, and also we want to integrate the solar cell system and the capacitor. And using that tandem solar cell, we want to apply and produce the green hydrogen. And also actually, when I was the undergraduate student, actually I studied that the optical communication and the photonic device. So I'm very interested to make that the quantum computing or quantum the communication. So actually the perovskite material is very useful to make the single photon generator or the single photon counter. So now I'm studying to the single photon count or the generator as well using the perovskite material. So the doctor already explained that the hydrogen economy of that world case that I just focused about the Korean case. Actually, the hydrogen can be classified to the gray, to the blue or green, but we are interested to synthesize the green hydrogen. So green hydrogen can be synthesized by the photocatalyst or PEC system or the pure cell. So, but we are focusing on the PEC system. And also the hydrogen is very small. So through the hydrogen production, and then we should develop transportation and storage and utilization system will be developed. So I think that the ideal technology to realize the carbon neutral is that the realization of hydrogen economy by a cost-effective production. In Korean government target is that we should produce the hydrogen below the $2 per 1 kilogram hydrogen. And also, so to realize this one, the photovoltaic system should have the efficiency more than 35% to or 40%. So by using the single junction solar cell, we cannot obtain over 35% system. So we should make that tandem system. So and also the hydrogen very low weight energy storage, high the weight energy storage system. So we should develop this as well. So Dr. No already showed this one. But we are focused on this the tandem system. More specifically, the LONGi, the China company, reported that the record efficiency about 33.9%. The size is about 1 centimeter, square centimeter. And open circuit voltage is about 1.966. And the short circuit current density is of 20.76. And field path is very high, 83. So, and about several days ago, they reported that the efficiency is about more than 34%. So the efficiency is very high. So we just think about how can you make that the highly efficient the tandem device. The multi-junction solar cell can be classified to 2 or 3 or more than the 3 junctions. So the structure is like this one. So in 2 junction tandem solar cell case, generally the bottom cell can be usable to silicon, perovskite, and the CIGS and the quantum dot as well. So based on the theory, so when we fix that the silicon at the bottom cell, the record efficiency will be about in between 36 to 40%. So, and also we make the 3-junction system we can obtain about 50% of the efficiency. So we start to make that the two-junction solar cell. So, but the ideal, the band gap of the perovskite material case, the band gap is about 1.75. So the absorption onset is about 700 to 750 nanometer. So actually, the highest efficiency of the single junction perovskite solar cell is composed of the organic inorganic hybrid perovskite. But basically, the organic material has low for the thermal stability. Because in silicon solar cell case, to make that lip-on electrode, the firing is necessary. So the organic material is not applicable. So that's why we are just focusing on the full inorganic perovskite solar cell material. So based on that scheme, the session PV I3, all inorganic perovskite material is ideal. So we started to fabricate the all inorganic perovskite solar cell. Basically, we started to use that session PV I2PR material. Then to extend that absorptivity in the long wavelength, we just sprayed and we made a graded structure. Then we can extend the absorption bandage to the 700, about 30 nanometer. Then at that time we can get about 17% of the efficiency. But the session PV I3 had the good thermal stability, but it had the poor phase stability. And also it had the poor moisture stability because that sodium iodide is a very hygroscopic material. So we should protect that moisture invasion to maintain that it's the phase structure. So we need to make that the black page like this one, but in most cases, the black page is easily to change to the non-perovskite yellow page as well. So we should add some the additive material, and also we need to make the protection layer with the barrier property is necessary. So we divide that use the oxidized MXene layer to protect the perovskite layer. So actually we have studied the MX and MXene. So generally we synthesize the titanium aluminum carbide MAX system. So this is the commercial one and this is the homemade one. So we can synthesize the very large area, the MAX. And also we can exfoliate the MAX to two-dimensional MXene. So actually this is the titanium carbide TX Maxim is the two-dimensional nanotube structure, so it had the very good barrier property. And also the titanium carbide, the bond had the good, excellent conductor. So the electron transport is very good. And also if we partially oxidize that, the surface of this MXene, then it changes to titanium. So titanium is a good electron transport layer. So by combining this concept, we made that the composite layer of the perovskite, and this is the partially oxidized the MXene layer. So this is the characterization of O-MXene. So through the oxidation, this is the TM imaging, and this is the XPS imaging. So the surface is the partially oxidized, and finally, through the full oxidation, it is wrapped and then changes like this one. The color also changes from the black to white. This is confirm that oxidation of the MXene layer. This is the XPS. This is the oxygen and the carbon and the fluorine. You can easily follow that the titanium layer is gradually formed. This is the blue one. Yeah, you can see that. And also the carbon layer, the titanium carbon layer is gradually decreased. And the surface is also terminated by the fluoride. And finally, it changed to a titanium fluoride layer. So another characterization of the MXene is the XRD and the Raman and the UV visible spectrophotometer. So you can easily follow that. About the MXene is the fully disappeared about more than 12 hours oxidation. So we can synthesize partially oxidized one about in between 3 to 6 hours. So this UPS and this IV for conductivity, so we can characterize that they're the properties. So when the MXene, actually basically like the graphene, the MXene is the conducting material. So about less than 3 hours oxidation, the MXene had the conductor properties. So the conductivity is high. But over the 6 hours oxidation, the MXene is changed to the semiconducting material. So they had that the balance band, and so from here we choose that the 6 hour oxidation MXene. So this is the band gap. So it's the 3 hour, the oxidation is the best to use that concept. So we made that session PbI3 and O-MXene, the composite layer on top of session PbI3, like this one. So from here, this O-MXene layer fully extracted the electrons from the session PbI3. And also this device structure like this one. So we just add that the composite layer in between the session PbI3 and the electron transporting layer. So, and also this is the work function and Lumo level. So this is the result. So by through the partial oxidation, we can gradually control the electronic structure. So finally, we can get about the 10%. We can get the highest efficiency. About at that time, this is the highest efficiency. And through the formation of this O-MXene interlayer, so we can strong potential buildup in this active layer. And through this the O-MXene layer, we can promote the charge separation and also charge transporting as well. So through this barrier property, this O-MXene layer improve that the device stability as well. So in this case, about the humidity case, the controller is easily died, but the O-MXene layer is maintained their efficiency. So finally, this O-MXene layer has the good long-term stability as well. So this is the certification. And then finally, we applied that the inorganic perovskite to make the multi-junction solar cell. So this is the silicon, and the perovskite, and the perovskite in silicon solar cell. We get this efficiency about several years ago. So currently, it's more than 30%. So I think that using the tandem system, if we applied the tandem system to production of green hydrogen, it will be competitive to the partial pure as well. So I finalized this talk. Thank you.
Thank you for your nice presentation. This is the end of whole three presentations, and we will move on to the wrap-up discussion. Professor Hong is now in charge of the wrap-up discussion. I will hand over my mic to him.
Based on our schedule, we do have only like less than 20 minutes. So I'm not sure even we need to have this set up, but I think, we already have, setting this one up. So we're going to wait for this setup. However, if you have any question regarding those three presentations that we made from Korea University, I'd like to have your questions. And if there is no questions from the floor, then I'm going to have a couple of questions, since we don't have enough time. What I like to do is I like to make questions to the professors from Yale University. A couple of things. Number one is where are we going to go from now on? I mean, we talked about what we do today. I'd like to develop collaborative, future work out of this event between Korea University and Yale University. So I'd like to, get your opinion or your, thought about how we're going to proceed, how we're going to develop collaborative, research project or other things like educational, the program based on what our discussion today. That's the first question. And the second thing is, I'm Professor Kim and also Professor Gary Brudigu. Is that correct? I always have problem with your last name. I think I'm going to practice more. And so I like to call you Gary. And you mentioned about, your student actually made, companies out of, the technology that you developed in your lab. And we are talking about climate technology here to combat against climate change. But at the same time, we are developing climate technology to transfer our technology in the lab to real applications. And then, possibly we can make money out of it. I mean, big money, if possibly, or hopefully. And I'd like to have your recommendation or your suggestion for students or even professors at Korea University who likes to do that, who likes to develop climate technology in order to help, Earth, but at the same time, transfer this technology to, real world and then possibly making big money. How we can do that? And that is my second question for both of you professors. So let's sit down here. So I made the questions already because, I tried to save my time because we have limited time left. Okay, Gary, I think I'd like to ask you the first question first question regarding where we're going to go from here.
Yeah, so I think there's some very exciting possibilities of collaboration. So one of we heard two really fantastic talks about perovskite solar cells. And we have several people in the energy sciences who are also working on perovskite solar cells. So that certainly is one area of collaboration. And then another aspect is the work on catalysts, and they need to be coupled to photovoltaic devices to be able to do, light-driven water splitting or light-driven solar fuel production. That's another area, I think. But one of the first steps perhaps could be some student exchange programs. Having students from Korea University come to Yale for a semester to work in the lab, or maybe Yale students coming to Korea University. So I think those are some suggestions.
Thank you very much, Professor Kim.
Gary mentioned his approach of putting people from different fields into one space, and that really creates the innovation, right? So at Yale Environmental Engineering, we used to have a separate labs, but now all the labs are merged together, and the student spending time together, eating lunch, and drinking coffee together, that really has been, one, sort of starting point for a lot of collaboration. At Yale, my major is environmental engineering, and it used to be at Georgia Tech, civil and environmental engineering. And when I came to Yale, I belonged to chemical and environmental engineering. And I started to work a lot with chemists. I actually have a paper with Gary too, 2 papers. And I do a lot of collaboration with a computational chemist because I have a lot of questions that I cannot solve. One of the biggest collaborator now is a physicist who does X-ray. So that sort of environment really created the collaboration. Now we are talking about energy and water. I seriously do not understand much of perovskite. But I think at the beginning it's extremely uncomfortable, like listening to what I don't understand. But that contact, the personal contact over time pays off. So I agree with Gary that the exchange of people, even though it takes time, is really the key essence of discovering new collaboration.
Thank you very much. I think the Professor Kim and myself, I think we work together in the water sectors, and especially seawater desalination. Not seawater desalination technology, and also possibly advanced oxidation process development. And however, we like to do more. Not collaborative work between among water people, or collaborative or work among energy people. I like to have energy and water combined collaborations, and I think this is the future of our collaboration between Yale and then Korea University. I hope today's this seminar or forum or in the discussion that we are making right now is a basis for making this kind of effort. And with that, I'd like to move on to the second question that I had. Transfer the technology that we developed in the lab to real applications. And then in that process, maybe we can be rich, Okay, Gary.
Yeah, I think there's that's really an important objective. We all talk about solving the energy crisis and climate change, and research is great and breakthroughs are great, but you actually have to have companies that apply this, and so who will start those? And my experience is that you need the right type of person. It's not something that just happens by sort of taking someone and say start up a company. So I mentioned Staff Sheehan, who started up this company, Air Company. He really is a businessman at heart, and he did a chemistry PhD to learn the chemistry, but he really wanted to be to do startups. So you need somebody like that, I think. But you also need to have the science that can actually be applied for a successful company, and that can be done through patents and licensing. That doesn't necessarily have to be new startup companies, but both are important.
Okay.
Right. Robert Langer at MIT is pretty renowned professor who launched a lot of startup companies. he said that it's really about the investment on people. So what I mean by that is that the staff, who is a superstar, startup, entrepreneur that Yale has created, actually has been coming to Yale a lot. I've been also interacting with him, and my students got heavily influenced by the staff. So I had one slide showing the students starting a company out of the technology that we are working on. That person, actually, he showed interest in research as a freshman in college, or much younger than you guys when he first started. And he's now a CEO of company as a junior of college. And the way I see is not really an investment of my time on that particular product that I have now, but more on that particular student, because I keep telling him that you may fail in this first material or product, but you're going to continue to advance for next many years, building up many different companies. So Yale has that infrastructure and educational system to really focus on people investment.
So both, professors are talking about we need to have, people with a heart or business mind, and I think that's you. I mean, you guys. I mean, if you have a heart and then also business oriented, I think we can do it here, and also with the collaboration with foreign, prestigious institution or university like Yale, we can do a lot of things. We can achieve technology innovation as well as making business out of it. I hope that today's seminar and forum that we had so far is the basis for making this kind of outcome. And Yale University has some kind of supporting system to make professors and students making business or the developing company. Do you have any special program incubating the company?
Yes, so Yale recently launched an organization called Yale Ventures. So we used to have some sort of scattered organizations in the past, but now we put together organization to really promote entrepreneurship. I just recently started a company. Yale actually does not allow professors to be on the board. I cannot be a CTO or CEO because my primary job is teaching and research. So my student, junior, he's a CEO, and CTO is my PhD student. So we went through all this process of the venture, speech, and etc. etc. When we were filing a company, Yale Law School came in and they did all the work. So actually, from my side, I didn't do much. It's actually really Yale's organization helping at the multiple fronts. Of course, tremendous amount of time investment from the person who wanted to start the company. But anyhow, just going back to what you are saying about making money, right? And so I've been keep telling my student James that I want you to make billions. But I just want that the changes, and that could be millions. So it's really about my students, our students, to really become entrepreneur with big dreams. I think that's what university should do.
I think the oldest seminar that we have today, without Professor Song in the audience, and without his effort, we couldn't do this. We couldn't put this one together. So I'd like to give him big applause. I mean, the big hands. And he's a director of international affairs at Korea University. And I'd like to, ask that. My last question goes to you, and because student exchange at graduate level is, I think, easy to do. I mean, we can make, student visiting, lab each other. But however, if we go further than that, and for example, we like to make some kind of, the joint program, I mean, official educational joint program at the level of graduate school as well as maybe undergraduate level. I don't know whether or not that could be possible. So based on your experience, what we need to do to strengthen our relationship with Yale University.
Wow, as a alumni of Yale and alumni of Korea University, I'm thrilled to have this kind of wonderful forums. Well, actually, this is a second forum, and the third one will be in our medical school, maybe in October. And next year might be our 120 years anniversary. So we want to invite a new president of Yale University, and the theme might be about next intelligence or human intelligence or artificial intelligence. But I think that this forum on sustainability is really crucial on concluding the exchange of graduate students by having this kind of forums. So little by little, I think by making this meaningful forum in each study area, we can expand the exchange of graduate students, also undergraduate students, if it can be possible. And then with University College of London, we are having co-seed funding research collaboration programs. So it's basically for junior faculties on specific fields that both institutions agreed on that. I think with Yale, we can do the same thing, like UCL model. And with medical school, I think there is a lot of progress in terms of internship and MD, PhD exchange and educational programs. So, thanks for this Yale-Korea University Forum. Our expansion with collaboration with Yale is actually progressing and expanding a lot. Thanks for your all efforts. Thanks.
Thank you very much. Very, very good comments, and also encouraging comments. I think the both presidents from both universities show enthusiasm to make this relationship even stronger. And so I think I have a hope that you have all those plans for next 2 years, and then I guess we can combat against climate change together, and then we can have better future, sustainable future for next generation. I think that, we're talking about making, business out of it, and we can be rich. But bottom line is, we work together to combat against climate change, so that our next generation will have, comfortable life. And I think that's the bottom line, that we can work together. With that comments, I think the time is up already. So this will be my closing remark. And I think, if we have time, then I can have more questions from the audience. And so any question or comments from the audience? Student, I think we have, all students right now. If we don't have any questions, yes, we will have, another seminar tomorrow, specifically designed for students, at 4 o'clock in engineering school. So at that time, you guys feel free to ask any questions, okay?
I just want to make a comment that Yale prefers to have students who want to ask questions, who likes to talk.
Yeah, doesn't matter. it doesn't really matter whether or not that is a stupid question or smart question, whatever. I think that we can communicate better with your questions and comments. Okay, then I'd like to, I guess if there's no further comments, then I'd like to wrap up and finish this forum. Thank you very much.